Hey, Mike.
Hey, Moshe. Give me 1 second.
Hey, I see that.
Hey, Jimmy.
I'm sending an email.
I'm glad you can join us.
Yeah, no, I'm sending him an email on something else. Oh, okay. Oh, there we go. Hello, gentlemen.
Hello.
So, Moshe, are you giving your guest presentation first?
Very briefly.
Oh, okay.
Yeah, it'd be good to go first, definitely.
What about tomorrow? Are you? It's just your presentation, or?
Yeah, it's going to be my presentation. It's not going to be very long. It is really amazingly simple regarding the impact of the topic.
I'm sorry, regarding what? I didn't hear you.
The impact of the topic. The fact that there have been observations of superluminal motion, that when particles cross a tunnel through a potential barrier, they move faster than the speed of light. This is probably one, if true, it is one of the biggest, most startling developments in the past many, many years. I would say the most striking development since the discovery that neutrinos are faster than light. I suspect it's probably in the same category. But
Yeah, but that's been dispelled.
I know, exactly. That's my point.
No, but here's the thing. I read the paper you sent, and he answers this question. The Heisenberg uncertainty principle can explain this because they're measuring, in these experiments, they're measuring the group velocity of the wave function. And the group velocity does not necessarily tell you exactly what the position is. It's only probabilistic. But the other thing is superluminal does not mean acausal. Entanglement, for example, is superluminal, but it's still causal. So you can't go back in time. There's no way you can do that.
Yeah, I read the Quanta article. It was very interesting. I gotta look over it again. I mean, it reminded me of like, I'm taking this class right now, and I was a bit surprised when the professor mentioned this thing where he was like, we're discussing like the early days of quantum mechanics, and he was, deriving like wave equations from sort of first principles and stuff. And he was like, if you think about, like at the time, like the de Broglie wave of like an electron, and you think about its like particle velocity and then also like its wave velocity, that like those two velocities together have to multiply to c squared. And so for like a photon, both are the same. The particle velocity and the wave velocity are both c, so you get c squared. But it implies that for, like a massive particle, if the particle velocity is less than the speed of light, then the wave velocity actually has to be greater than the speed of light. And I was like struck by that. I'd like never really thought about that like before.
No, but here's the thing. When you're talking about a wave function is probabilistic.
Yeah.
A wave function,
exactly.
Waves. Typically, wave velocity is the group velocity of the wave. In other words, the velocity of the peak of that wave. But that doesn't describe the speed of an individual particle, because the speed of an individual particle is probabilistic. It could be anywhere along that wave, not necessarily at the peak. By the Heisenberg uncertainty principle.
It seemed like from the Quanta article that they were like trying to find a way to like formulate how to like measure the time or whatever, like given that like fact that you say, Michael.
But they're measuring the group velocity.
Sorry.
They're measuring what would be the group velocity and assuming that's the velocity, when in fact it does not apply to quantum particles.
Yeah, that was my intuition too. I'm curious what we should read like the actual papers or whatever.
Can I Fourier transform this conversation?
Absolutely.
Look, as long as you don't have an infinite potential, the Schrodinger wave of any particle has to cover all of space. And no matter how small the probability is somewhere, if you find it somewhere and then later you find it somewhere else, there's always a finite probability that it be infinitely far away the second time. So as long as there aren't infinitely high potential barriers, you can always find it far away. So exactly what you mean, what you think you are doing when you're calculating the speed of something becomes very unclear because of this of the spread out of the wave of the position.
Right, and to calculate the speed, you have to make an initial and final position measurement, and both of those measurements are probabilistic. In fact, if you have a potential barrier, the particle could actually be through the barrier initially, because as you said, Andre, the particle is spread out over space. It could actually already be through the barrier. So how are we measuring time? You know, it's, yeah, over many particles, then probabilistically, you know, this should all come out in the wash. But for individual particles, you can't measure position and velocity for an individual particle.
Andre, what you said is true for a particle that has always existed. Suppose you create a particle right now, or suppose you create a molecule right now. You have a chemical reaction taking place right here, right now. A new molecule got created right here, right now. This molecule never ever existed before. And right now, the probability of finding it some distance away from here is pretty much zero.
Pretty much zero. Exactly right, Moshe. Pretty much zero. At the instant that it's created, its wave is non-zero everywhere in space. Everywhere.
Well, that's according to non-relativistic quantum theory, but according to quantum field theory, the particle is an excitation of an existing field that has always existed.
That's right, and so let's go to quantum field theory. But even in standard quantum mechanics, since all these particles are identical particles, you don't even know you're measuring the same one. All you're doing is measuring something, saying, "Oh, I found an electron here," and then later on you say, "Oh, I found an electron here." Well, there's no proof. There's not even a meaning to saying, "Is it the same particle?" All you do. So, what's the surprise that you find it here, and then you find it somewhere else? You measure an event here, you measure event A, and you measure event B. And if you're thinking classically and you say, oh, something went from event A to event B, the speed was greater than the speed of light. But if you're thinking, as you say, Michael, probabilistically, but what I would say is quantum mechanically, then it has no meaning to say, oh, it moved from here to there.
Also, and let's say something.
Electron. You had only one electron, and that's it. You don't have many particles, just one.
And you can't measure its position or its velocity with absolute certainty.
Of course you can.
That's Heisenberg's uncertainty principle.
Yeah. So
no, Michael. You can definitely measure its position and velocity. You could measure everything.
Not simultaneously.
You'd know I just got this value at this time for this case. That's what you would know. And then when you make another measurement, you would just say, oh, so the first time you'd say, I found an electron here with this position and this velocity. The next time you'd say, I found an electron here with this position and this velocity. All Heisenberg's uncertainty principle says is if you do this a lot of times, the spreads of these things have to be greater than h bar over 2. But that's not the issue here. The issue here is for one particular particle, what is its speed? And you can't even talk about what it means for one particular particle. All
Andre, you're saying
event.
you can measure the position and the velocity simultaneously?
Absolutely.
Doesn't that violate Heisenberg's uncertainty principle?
No, it does not, because as I've said a number of times in this group, all the uncertainty principle says is it puts a restriction on the spread of the position and velocity of repeated measurements of identical preparations. That's all it does. It says if I prepare this an ensemble number of times and I measure the position and velocity, then you look at the spread and the position, you look at the spread and the velocity, and you say, you know what? Their product has to be greater than h bar over 2. That's nowhere near putting any restriction on finding the exact position and velocity of one case of a choice from that ensemble. When you pick from the ensemble, you measure exactly the number of position, exactly the number of the value for velocity, and then when you pick another time, you prepare it again identically, you pick it again, you're gonna get this spread. That's what it tells you. It emphatically does not say that in any particular measurement, you can't get an exact position and velocity.
All right, but here's the thing. The article that Moshe sent, I think, and I read it a few days ago, it implies that that if you have superluminal, speed, that it could be acausal. You could go back in time. That's not, theoretically, you could have superluminal velocity, but it's still causal.
Well, I think they sort of raise that question. I mean, they don't straight up like say that something
They imply that this implies you can go back in time. That's crazy.
No.
I mean, I think certainly it's non-intuitive what they find. Like, I'm just looking at it now, like this is, I mean, depending on your intuition, it's like, I think this is surprising. Like when a particle tunnels, the trip takes less time than if the barrier weren't there. If you thicken the barrier, it hardly increases the time it takes for a particle to tunnel across it. And this means with a sufficiently thick barrier, particles can hop from one side to the other faster than light, traveling the same distance through empty space.
This is an incorrect measurement. It's an incorrect measurement.
I think there's like some deep, like interpretive questions, but like it is certainly cool. I mean, it's like, it's definitely.
You don't really know what you're measuring. This is the problem. This is like the neutrinos going faster than light. The experiment was set up incorrectly. Or this thing with this classical perpetual motion machines. People are always designing perpetual motion machines.
I mean,
the fallacy is that their measurements are incorrect.
I would say it's the interpretation of what you're doing. So if that's what you mean, the measurements are incorrect. What you're doing is you set up a situation where you put a particle, you prepare something where the wave function says the particle can be found inside some box. And you say, oh, look, it doesn't have infinite walls, so it has a certain probability distribution that leaks out to the other side of the box. And then you do a measurement. You maybe have to do a number of measurements, but eventually you do a measurement and you find a particle inside the box. And now, immediately after, what's the wave function of that particle look like? It has a probability outside the box. Now you do another measurement and you find a particle outside. You find, I don't want to say I want to say a particle outside the box. So now the question is, what's the interpretation here? The interpretation, I think, is in the initial case, There was a probability of finding the particle in the box. You made the measurement, and you happened to find it there by the throw of the dice. And then you made another measurement. There was a probability of it being outside the box, and by the throw of the dice, you just happened to find it there. And now you got to switch over to some classical thinking about particles moving and particles keeping their identity. And by switching out of quantum mechanics, then you could write delta x over delta t is greater than c. And you say, oh, wow. And I say, no, you switched to classical thinking. There was no reason to think that way. These are just two separate measurements and that are consistent with quantum mechanics of finding the particle in one case with a certain probability, and you found it here. And then there was another case where it had a certain probability and you found it there. That's the way to think about it, and not moving back to classical thinking of trajectories of particles.
Andre.
Yeah, I feel you, Andre. Yeah,
I agree too. Although my interpretation would be slightly different. The probability of a particle being inside or outside the box, there is a probability distribution for that. Once you make a measurement that the particle is inside the box, there's no longer any probability that it's outside the box. Once you make the measurement, the wave function collapses.
It's
Instantaneously, but a finite amount of time later, it has a probability of being outside the box.
Not the same particle.
At the instant the wave function collapses, you have the particle at one point or inside some small volume, depending on how you made your measurement. And that's where it is. The wave function has collapsed. Everywhere else, it is zero. If I have only one electron and that's it, there's nothing else in the universe, and I find right now this electron at this corner on my desk, right now the probability amplitude of finding it at the opposite corner on my desk is zero. The probability amplitude over there just collapsed to zero, just as it collapsed to zero everywhere else in the universe.
Yes, Moshe, but an instant later, it is spread out across the whole universe. An instant later, any finite amount of time later.
No, not quite. It propagates at the speed of light. You have a wave packet that spreads not faster than the speed of light. It is true that the wave packet starts spreading immediately. As soon as I made my measurement, the wave function has collapsed. And as soon as I made the measurement, now the packet starts spreading. But the spread
Moshe, think about what you're saying. Think about what you're saying. I have a wave. I have a wave that you're saying has exactly, not approximately, exactly zero amplitude, a certain finite distance away. There is no such wave. There is no such mathematically continuous analytic function that works that way. No analytic function works that way. So if you want to give up analyticity in physics, you could say what you just said. But as long as you have analyticity, then the instant later, it is everywhere.
This is why wave function collapse is a fiction, because this is a part, again, of quantum mechanics. Once you get to quantum field theory, then the whole thing is about the field, which is always spread out, and it's the field changing. You have particle creation, particle destruction as part of the field. So, you know, these singularities don't exist in the sense that they do in quantum mechanics.
Why don't we, Moshe, why don't you talk about your special relativity?
Okay. What I wanted to bring up is something that we discussed last time that had to do with entanglement, with Bell pairs, and whether or not this violates causality. By the way, this is something that we've discussed already at least once before in the New York Quantum Theory group. So I'm going to go over it very quickly. Is there any way I can put my screen on?
Yeah, yeah.
Right now I cannot do it.
Here, give it a try again. I just enabled it.
Okay. Okay, let's start with special relativity. The two special relativity consists of just two axioms. It is incredibly simple. The law of physics are the same, they're identical for all initial observers, and the speed of light in vacuum is the same for all observers regardless of their velocity. That's it. There's nothing else to special relativity. We can add all kinds of doodads to it, but if we don't, but this is what special relativity is, and this is what we're going to focus on. And focusing on just those two axioms is very simple. They lead to Lorentz invariance. Lorentz invariance is an unavoidable consequence of just those two axioms. Once you have Lorentz invariance, it tells you that the mass of a particle, which has a non-zero rest mass, is given by this formula right here, which shows you that as the speed of the particle approaches the speed of light, the denominator goes to zero and the mass goes to infinity. Therefore, a massive particle cannot travel as fast as the speed of light. It will always travel at a lower speed. And of course, light itself travels always at the speed of light, not more nor less. This is one of the axioms of special relativity. So light travels along the light cone, everything else travels inside the light cone. This is what special relativity tells you. To say that information cannot travel outside the light cone is not part of special relativity. This is something that you get only if you add another assumption. If you assume that the only way to transmit information is by transmitting energy, then yes, then information can only travel on or inside the light cone. But the fact that the transmission of information requires transmission of energy is not built into special relativity. This is an extra feature that has been added. Now, there are two reasons why this extra feature has been added. One reason is because of the Bekenstein limit, which tells us that if you have a certain amount of information, then you need a certain amount of volume and a certain amount of energy to instantiate this information. There's a lower product of energy times volume for a given amount of information. But here we're not talking about storage of information. Here information just got exchanged between two events, and we are going to look in particular at two events that are outside each other's light cone, that are space-like separated. And another reason why we take it for granted that transmission of information requires transmission of energy is because we simply don't know of any other way of transmitting information. Either we transmit it by electromagnetic waves, or we transmit it by old-fashioned letters written on paper, which means there's matter that's being exchanged, and this is always inside the light cone. But just because we don't know how to do it doesn't mean that it cannot be done. And we know that it can be done in the case of Bell pairs. If we have two entangled particles, one of them can be here, the other one can be over there. They have a space-like distance between them. And once let's say the spin of this electron right here has been measured, it immediately determines the spin of the electron over here.
Moshe, can I say something?
Go ahead.
Energy cannot be transferred faster than the speed of light. With entangled pairs, you're not transferring energy. Energy cannot be transferred faster than the speed of light. And according to Landauer, information is physical, which means it requires the transfer of energy. So that means that information can never be transferred faster than the speed of light. The light is the upper limit to how fast we can transmit information, because it's the upper limit to how fast we can transmit energy.
Well, you just said again what I just said. You just repeated what I said.
No, but I'm saying that, you know, people are thinking that maybe there's some other way we can transmit information that's faster than the speed of light.
Now, let's look again at the case of entanglement. Suppose we have a belt pair, one electron here, one electron over here. The two of them are in the singlet state. I make a measurement here, it immediately affects the electron over there. This kind of measurement, this kind of experiment has been done gazillions of times. And there's not been one single instance where the experimenter has detected that any energy has been flown, has moved from one electron to the other or in the other direction, or from one photon to the other. There's no exchange of energy has ever been observed when those experiments with belt pairs have been done. So obviously, as far as we know, there is no exchange of energy here. There is no exchange of energy, so this can happen outside the light cone, and information in some way, and I'm going to come back to this in a minute, has been exchanged. We have to be careful about what kind of information. In particular, this is not going to allow Alice over here to send a message to Bob over here. Alice cannot send a message to Bob, hey, Bob, I just sneezed. This information cannot be exchanged. So the information that can be exchanged here, in this specific case with belt pairs, is very limited. And we're going to come back to this in a minute. But before we come back to this, once we give up the requirement that information exchange means energy exchange, then we can start to worry, well, if no energy is being exchanged, how about sending a message to the past? I just send information to my past light cone without using any energy, and I can tell myself yesterday what is the stock market today. Well, this is going to be a violation of the Security and Exchange Commission, so we're not going to allow it. So we are going to say, in addition to the two axioms of special relativity that we've just seen, we're going to add another constraint that no event can send information into another event inside its own past light cone. I don't know how to derive this from the two axioms that we have seen, unless you require that information transfer means requires energy transfer. So we can add this requirement, and if we add this requirement, this also implies that no event in my future light cone can send information to me right here, right now. So I cannot send myself information next week, from next week about what the stock market will be doing next week, and I would get the information right now. We are going to disallow this. Now, we are still left with the possibility that we can have an exchange of information outside the light cone. And again, it does not violate the axioms of special relativity. but we are going to put some restriction on it. The restriction is based on the fact that the only cases where we can observe, where we have observed such exchange of information outside the light cone has to do with entangled pairs. I never heard about anything else that would remotely look like an instantaneous exchange of information. So I'm going to add one more constraint, saying that two events outside each other's light cone can exchange information, provided that no energy is being transferred, only if their past light cones intersect. If their past light cones intersect, then they can be entangled. It doesn't mean that they are entangled, but this is a requirement to allow entanglement. Sometime in the past, those two could have interacted. Or maybe there's some event that is in the past of this event, and in the past of this event, and this event in the past has sent some information here, it has sent some information there, so those two events right now share some information.
Well, Moshe, what about like these like entangled vacuum phenomena?
Go ahead.
Well, you know, it's like if there's like an accelerated observer, then there might be some entanglement that can be harvested from the vacuum, which doesn't necessarily require, you know, past light cones having intersected. And like more generally, like I'm not sure it's always the case that entanglement requires, you know, like a kind of intersection of light cones, like an interaction. Like if, you know, like depending on like what the boundary conditions are, so to speak, you might sort of have like the, you know, as I say, like some kind of entangled vacuum state that different observers might have access to.
Okay, the reason I'm adding this kind of constraint, the two events outside the light cone can exchange information only if their past light cones intersect, is then the fact that the only example that we know of exchange of information outside the light cone is due to entanglement. An entanglement where indeed those two events were at the same point in space-time sometime in the past. Or if there is some event in the past that has sent information to both of them. Let me give you an example. Suppose that this is Alice, this is Bob. There is 1 light year away from each other. I am right here in the middle, and I'm creating a Bell pair of electrons in the singlet state. Well, I did it in the past. I sent 1 electron here, I sent 1 electron there. So right now, Alice and Bob, each one has 1 electron of the Bell pair that I have created. And right now, they are 1 light year away from each other. And let's assume for simplicity that they're not moving. Alice is motionless, Bob is motionless, and they're motionless right in the middle. And we all have agreed, and we all have identical clocks, and we all have agreed that at some given time, agreed upon in advance, after Alice and Bob have received the electron they got from me, they're going to measure the spin of their electrons in the z direction. And furthermore, we have agreed that whoever measures the spin up is going to enjoy a glass of Merlot. Whoever measures the spin down will enjoy a glass of Chablis. That's Alice is right now enjoying a glass of Merlot. She knows that Bob is having Chablis, even though it happens at the exact same instant of time. This information did not exist until Alice made the measurement here and opened her bottle of Merlot. The information did not exist. Right now, she knows that her electron is spin up, and she knows that Bob is having some Chablis. So you can say in this sense that yes, there is some sharing or transfer of information between Alice and Bob that is taking place instantaneously.
Sure. I was just pointing out that it might be that there may not have been a common event in the sense of like the creation of a Bell pair, but some kind of entanglement like in the field that had like always been there.
Look, the point is,
I'm
if
going
there
to
is,
come back to this. 1 moment, Matt. I'm going to come back to this. This
Okay.
is the whole reason why I bother to talk about this is precisely about something that you mentioned right now.
Uh-huh.
This is where the payoff is. That's where the pay dirt is. But at this point, the underlying point is that here there is a common event, and there could be something else. But the past light cones must have intersected. You can claim that this condition is superfluous. I'm just adding this condition because I
Okay.
cannot conceive of any other way of having this kind of exchange unless the past light cones have intersected, unless the past light cones do intersect. If you don't like this extra requirement, okay, maybe we can live without it. Living without it means that there would be a way of having instantaneous exchange of information between us right here, right now, and an event 20 billion light years away.
Yeah, and in any case, like my objection is sort of irrelevant in the sense that like if there's some rule, like, you know, one of us is going to drink Merlot and one of us is going to drink Chablis, like that implies that we have some prior agreement about like we're going to do a measure, how to interpret it and so forth. Yeah, so fair enough.
Yeah, exactly.
Moshe,
That's the
can you
point.
go back to the definitions you put up?
The axioms of
The
special
axioms,
relativity.
yes,
Okay, here we are.
right. I
Einstein looks good in that picture. Good looking guy.
I guess I think that number 2 is more appropriately stated that the let me say it sloppily and then I'll try to correct it. I would say the speed of causality. In other words, what you can control cannot go faster than the speed of light. That you cannot control, that things outside of your light cone cannot control you and you can't control them. So it isn't a question, the way you posed it, as about information or of the motion of light, and it's much more, it's more appropriate phrased as you cannot send a controlling influence faster than the speed of light. So, so often that incurs information, but as you're pointing out, depends on how exactly you define information is tricky. But so that's why I think that number 2 should be better phrased in terms of controlling influence rather than any kind of motion of objects or information, and it just gets around the kind of problem I think that you're bringing up.
Okay, this Wikipedia article gives you 2 distinct definitions of special relativity. This is the modern definition of special relativity. Those are the 2 axioms, and the word information does not appear anywhere in those 2 axioms.
And I appreciate that the word information doesn't appear, but I think that also the word light should not appear.
Okay, but it does. But the word light does appear, and it is critical here. Another formulation, this is Einstein's original formulation of special relativity, is given by the two axioms right here. It's a little bit more verbose. Those two axioms are equivalent to the two that we just see. This one says the principle of relativity, the laws by which the states of physical systems undergo change are not affected, whether these changes of state be referred to the one or the other of two systems in uniform translatory motion relative to each other. So again, this is the same as the first axiom that we saw before, saying that the laws of physics are the same for all inertial observers. And the other axiom is the principle of invariant light speed. The light is always propagated in empty space with a definite velocity, c, which is independent of the state of motion of the emitting body. That is, the light in vacuum propagates with the speed c in at least one system of inertial coordinates, regardless of the state of motion of the light source. Let me say it again. What the second principle says is the following. There exists at least one inertial system where an observer measuring the speed of light will measure the same speed regardless of the velocity of the light source in this inertial system.
Yeah.
So,
I guess.
and one moment, and because of the first principle, the same will be true for any other system with moving with a constant speed with respect to the system where this postulate is true.
Yeah, so I have, these are all my problems with these axioms. First, I feel like light is too restrictive. That really what I would claim the intent of relativity, of special relativity is, and is not, and should not bring up light, should not bring up inertial frames. All it should say is that I can't send a controlling influence in any way outside of my light cones. That's what it should say. And therefore, these questions of information, these questions of inertial frames are not relevant to the intent. The intent is what I'm saying.
Andre, you answered your own question, Andre. The way we transmit information, the fastest way we know is by energy transfer, and that is by electromagnetic communication. So how can you disregard light?
Andre, let me
I'm telling you how. We don't want to get involved with, we don't want special relativity to have problems with the Bell experiments. That's why I phrase it the way I did.
But that's not transferring information.
Andre, you can phrase it any which way you want. This is the way Einstein phrased it, and Einstein phrased it this way because he was concerned with the speed of light. This is something that he was concerned with since high school. But only after he got his PhD, finally he managed to come up with those two axioms. This is what he was concerned with, is the speed of light and Maxwell's equations, the invariance of Maxwell's equations. Now, for the purpose of discussion, I propose that we focus on special relativity, either using Einstein's initial formulation or using the more modern formulation right here. Those two sets of axioms are equivalent. And for the purpose of this discussion, we focus on this as being special relativity. Now, out of respect for you, Andre, what I've done already is to add another constraint to those two axioms. In particular, I mentioned that no event can send information to another event inside its own past light cone. This is what takes care of our most basic idea of causality. I cannot send any information to myself in the past. I cannot send myself information about the stock market today so that I can get it last week. I cannot receive information from the future right now. This is our most basic idea of causality. And if you do not insist the transfer of information requires transfer of energy, then I believe that adding this kind of constraint is necessary in order to assure causality. But we still have the option of sending information outside the light cone. If I send the information outside the light cone, there's no way I can convince my grandfather not to marry my grandmother, because this would mean sending information into my past light cone. So I'm not going to incur any of the paradoxes that come with violation of causality. But we still allow transfer of information outside the light cone. And even outside the light cone, I tend to add yet another restriction that, again, I don't see how it results from anything we've seen so far from the basic axioms. And the extra restriction is the two events outside each other light cone can exchange information without exchanging energy only if their past light cones intersect. If you don't like this restriction, okay. I don't really need it for anything else that I'm going to say from this point on. But to me, this is something that without it, it will not make much sense.
Question. Moshe, how do you send information outside of the light cone? Yeah, I'm lost.
With bell pairs, do it every time.
No.
Yeah, bell
Yeah,
pairs.
well, this is what Andre was pointing out, that there's these ambiguities about what we mean by
You are not doing it with bell pairs. You're talking about quantum teleportation.
No, don't put words in my mouth.
Well, what are you talking about? How do you do this with bell pairs?
No, Michael, I did not say quantum teleportation.
Then tell me, how do you do it with bell pairs?
I have two electrons in the singlet state, one light year away from each other.
Yeah, but is information just bits, or is information, as Andre says, like a controlling influence?
How are you sending information?
Clearly, there's bits that are being shared, but at the same time, there's no way anybody can control them.
Look, here's the point.
By what definition, that's not
information. I agree with you. I agree with you completely. Using bell pairs will not allow Alice to send any information to Bob. It will not allow Alice to tell Bob, hey, Bob, I just sneezed. But if you have a bell pair, one light year away from each other, if Alice measures her electron, it will immediately determine what kind of measurement Bob will get if he measures the spin of his electron.
Okay, here's the point. If two entangled particles are space-like separated, then there is no way to determine who made the first measurement.
Yeah.
So you can't say that if Alice makes a measurement, she's sending information to Bob, because we don't know. Bob could have made the first measurement. There's no way to determine that it's space-like separation.
Excellent point. Between those 2 points, there's no time ordering. There's no time ordering between events that are outside each other's light cone, that are space-like separated.
Right.
There's no way of saying who measured first. All we can say is that once one of them measured, the other one is determined. Did this one measure first? Did this one measure first? This depends on the observer.
All right, here's a question. How do we know that determination was not made before the measurement? How do we know that when two particles are entangled, it is already predetermined whether one will be spin up or one will be spin down?
This is because of the Bell inequality. If what you said were true, the Bell inequality would not be violated.
Michael,
Experimentally, the Bell
the best way to
inequality is
see this-
violated, and the violation of Bell's inequality tells us that there is no way the spins have been predetermined.
Michael, the best way to see this is in the Greenberger experiment, and it's explained very well in the, which book is that? I forget the title of the book. I sent it-
There's no way to determine whether the
That's
spins are predetermined,
No,
but we know the
what-
relationship. The relationship is predetermined.
Greenberger thing shows that
Not pre-Bell.
no way,
You're
there's no
after
way.
Bellum.
You didn't hear me. The relationship between the spins, is predetermined. Therefore, no information can be transferred.
The relationship between the spins is predetermined. That's right.
So no information can be transferred.
But the spin of either electron is not predetermined.
Okay,
One
But-
point.
but I'm saying the reason you cannot transfer information willfully is because the relationship between the spins is predetermined.
Yeah,
Alice doesn't know what measurement she's going to make, so how can she transmit information?
no. Alice and Bob have agreed ahead of time that when they measure the spin of the electron, they will measure it in the z direction.
Well, that's when the information was transferred. Beforehand, when they made that agreement, that's the only information that was transferred. The measurement doesn't transfer any information.
Well, Moshe, what's the punchline? I mean, I don't want to rush you, but I was hoping to get onto my SYK wormhole stuff by like
What's
5.
the punchline?
I appreciate, Matt. Let me,
The punchline is all cows eat grass.
Oh, cows.
how do I? Can you guys see a different picture now?
Now we see the top of what you had before, but not much else.
At worldline.svg. And it's
Yeah, same one, but
weirdly right
less of
there.
it. Different aspect ratio.
Okay, that's better.
Ah,
No, that's not what I want. This is not at all what I want.
Who was that? Heaviside? That good-looking man on top?
I don't know, this is a mistake. Can you see a hand-drawn picture right now?
nope.
No.
Okay,
No.
one moment.
We see wave numbers.
Oh, it's possible like when you shared your screen, you shared not the whole screen, but specifically your like Chrome window. So like try clicking the share screen button and it'll give you like different
That's the
options. And then,
problem. I do not see the share screen button anymore. It has disappeared. I don't see any Zoom
Hmm.
here. Let me see what else I can do. Zoom has disappeared, except for you guys. I can see you guys.
huh.
But
Oh,
I
it's
cannot see
hidden. Yeah, the rest of the stuff is hidden.
Well, here, maybe I'll share my screen for a second, which maybe will
Okay.
take your screen. Maybe it'll return your Zoom to you.
Or you
Okay.
can know how you did it.
Yeah. Do you see the bar now?
No. I cannot see your screen. I can still see my screen, and that's all I can see.
Yeah, same here. All I see is Moshe's screen.
Oh, really?
Moshe, that looks like,
Larmer procession.
it
Ooh,
looks like it's from tomorrow's. What you're showing us is what you're going to do tomorrow.
Yeah, but right now, what I would like to see is Matt's screen, or at least some sort of zoom. Let's see. What,
Okay, well, yeah.
one moment. Okay, I think. Okay,
All right.
we
Yeah.
are getting there. We are getting there. Share screen.
yeah. I'll meet you in the future cone.
Okay, so right
All right,
now
nice. Yeah, there we go.
a hand-drawn picture, right?
Mm-hmm.
Okay, what I have here in the upper right corner is percolation and annihilation in vacuum. Because percolation violates conservation of energy, this can last only for a very brief amount of time. This is the Schwarzschild radius of a black hole. As we get closer to the black hole, the gravitational potential energy becomes more and more negative. It is a negative energy. So the energy of a particle at rest becomes less and less. So here you have less of a violation of energy. So this pair can live longer than this pair. You get even closer. And if those particles are created at rest, they're going to live even longer. And eventually you can have a case of a pair creation, one inside the black hole, one outside the black hole. The one inside the black hole can have negative energy. By the way, at the horizon itself, the energy of a particle at rest is exactly zero. Basically, the gravitational potential energy balances exactly the rest mass energy of the particle. And the same thing is also true for an electron. An electron directed outside and located at the event horizon is not going to move. The event horizon is a null surface. As you keep going inside the black hole, the gravitational potential energy becomes even more negative. So you can have particles with negative energy. So now you can have a percolation, one particle inside with negative energy, its opposite, antiparticle, being created outside with positive energy. The two of them balance each other exactly. So the total energy of this pair is zero. So here we start with the particle creating a pair with a big energy. Here the pair has less energy, here the pair has even less energy, and here the pair has zero energy. And because it's a particle-antiparticle pair, all the other conserved quantities balanced exactly. They have opposite charge, opposite spin, opposite upper charge, opposite baryon number, opposite everything else. So creating this pair does not violate any laws of nature that we know of. It does not violate any conservation laws. And now, since this particle has positive energy, it can move away from the black hole. This particle with negative energy is going to fall into the singularity at the center. So because it has negative energy, the total mass of the black hole is going to decrease by exactly the amount of energy that is being carried out by this particle right here. The critical point here is that those two balance each other exactly. And the question is, how is it possible? If a particle with negative energy gets created here, there's no way it can tell this point outside the black hole about the fact that it has been created. If you have to, it is literally outside its light cone. Its light cone, by the way, is completely bent into the black hole. It is completely directed into the black hole. So there's no causal communication, causal in the more general sense that you are used to. There's no causal communication in the sense of sending energy. But the two of them can communicate based on what you have seen a minute ago. If you have communication of information without transfer of energy, you can have this kind of information communication outside the light cone. And this is what is going to happen here. This event is definitely not in the past light cone of this event. So information can flow from here to here as long as no energy flows from here to here. If you look at this event and that event, now let's assume that we also have a timeline, time going up vertically. And this is a bit of cheating because I started with a picture here, but this is only space. There's no time here. But if I'm going to put a time on a vertical axis here, then we are going to see that this past light cone and this past light cone are going to intersect. In particular, before the black hole even formed, maybe this black hole is the result of the collapse of a massive star of 10 solar masses. It has collapsed into a black hole. Well, before it collapsed, this point in space and this point in space could very well have interacted. There's a very good chance that this point in space and that point in space are entangled. And Matt, this goes to your question before about entanglement in vacuum. Right now, here I have vacuum. There's nothing in here. But this point in space in the vacuum is still entangled with this point in space. So if we have what I call the restricted causality, I had a better word for it, I can't remember it. Minimalist causality. If we stick to minimalist causality, and by minimalist causality, what I mean are the two principles that we've seen before, the two axioms of special relativity. We do not violate the axioms of special relativity by making sure that those two events are correlated.
Moshe, can I give you an alternate interpretation here? Look, as I see it, what's happening here is some probabilistic event, there are two probabilistic events happening. One coming into existence on one side of the event horizon, the other, a particle coming into existence on the other. And conservation of energy then is not taken to be as a point conservation law, but a global conservation law.
Exactly.
So therefore we would say, look, possible events are happening all the time. They're just censored by a global conservation law. And that's why the only ones that happen are the ones that pair up like this, but it doesn't mean that they are communicating in any way.
I do not disagree with you. This may be another way of saying the same thing. It's another way of saying the same thing. It's another way of viewing it. And the bottom line here, there are two things that I want to highlight, which are the following. Number one, Bell pairs should not have any negative interference with your sleeping patterns. Don't lose any sleep over violation of causality in Bell pairs. Bell pairs do not violate special relativity.
Bell pairs are entangled.
What?
Bell pairs are entangled.
Yeah,
That's why they have nothing to do with special relativity. They're entangled.
okay, fine. They're entangled, that's it. So there is no violation of special relativity in Bell pairs, number one. Number two, there's no violation of special relativity in having information coming out of a black hole. When this particle comes out, and this is a particle, it's a real particle, not a virtual particle, just as this particle is a real particle, not a virtual particle. When this particle comes out, we detect it, we measure it. And therefore, we know that its counterpart has been created inside and is falling inside the black hole. So by measuring this particle, we have information about what goes on inside the black hole. And this shows us that we can have information coming out of the black hole, or it looks like it is leaking out of the black hole, depending on the language that you want to use, but we do not violate the principles of special relativity. We do not violate minimalist causality.
Moshe, it's not clear to me you have enough information coming out, because just because you saw that one particle going to the right, what do you know about what happened going in? You don't know necessarily that it was only one particle. It could have been one particle and a photon, and now they're at different angles.
Excellent point. Excellent point. For instance, let me make it even stronger. We look at this particle, and this particle may be perhaps a neutron. This is a neutron. What we can have here is an antiproton, an electron, and a neutrino. When we see a neutron here, it doesn't mean that we have an antineutron. Maybe we have an antineutron, or maybe we have an antiproton and an electron and a neutrino, or we can have some other combinations here. This is absolutely true. But what we know is whatever it is that we have on the inside must exactly balance what we have on the outside. We know the quantum numbers of whatever it is that has been created on the inside.
Question. So what happens when the inside particles are destroyed at the singularity? What happens to the outside particle? By your logic, it should also be destroyed.
Why? Why? Those two particles, they go their own separate ways. And
But if you have conservation of spin, you have conservation of lepton number, baryon number. If the inside particles are destroyed, all of that information should be destroyed outside too.
Let's look at it more carefully. Maybe this is a baryon, like a neutron, and this is an antibaryon, like an antiproton.
Mm-hmm.
I go outside here and I'm going to detect my neutron. So I know that I got a neutron out of the black hole, or it looks like a neutron came out of the black hole. And again, you have to be very careful here. This neutron did not come out of the black hole. This neutron came into existence outside the black hole. But it looks, when you are far away, hey, I just caught a neutron that came to me from the black hole. And at the same time, an antiproton was created here, and the antiproton was destroyed. Altogether, the total baryon number has remained the same.
No, it hasn't. You started out with baryon number 0. Once the antineutron is destroyed, you're left with baryon number 1. What happened to conservation of baryon number?
Well,
Yeah.
that obviously assumes a lot of theory about black holes. I mean,
This is
Well,
about
this is why I don't believe
whether
in
black holes
singularities
have
at
any hair.
black holes.
This is about whether black holes have any hair. So the question is, we know that a negative charge has to balances out a positive charge at the singularity. And we know that negative energy balances out positive energy at the singularity. But the question is here, do other quantum numbers balance out? So when you're adding a fermion number, does that balance out with a -1 fermion number on the at the singularity? That seems to violate that black holes have no hair. It seems to say that, oh, fermion numbers are part of the information that we have about the black hole and what's at its singularity.
The whole concept of the singularity violates every single conservation law that we know. Because everything is destroyed at the singularity, but what's outside of the event horizon remains the same, doesn't get destroyed. That violates every single conservation law.
Okay, let's look at this simpler picture, Matt, to get to your point. Suppose that you have an electron coming out here with an electric charge -1. A positron was created here with an electric charge +1. If indeed this positron gets completely annihilated, what we are going to see from the outside is a negative electric charge coming out of the black hole. The positron is coming out. But by the same time, when this electron, this positron was created, this black hole has acquired a positive charge that balances this negative charge. So at the moment of creation, there's a perfect balance. Now, what happens when this electron falls into the singularity? Well, according to black holes have no hair, electrical charge is conserved. If this black hole just gained here a positive charge, okay, so the
But lepton number is not conserved. What about lepton number? That's not conserved.
okay, you got a point here. You got a point here, and this is an issue that we all have with the black hole. As you mentioned, the singularity violates many conservation laws. And yes, in this sense, there will be a violation at the singularity, but there will not be a violation at this point. When the two particles are being created, everything is conserved. This is perfectly kosher.
Moshe, I'm sorry, I have to leave. I hope to continue this at some other point. I'm sorry. Goodbye.
Have a good night.
Hi, Andre.
Okay.
Well, this is why people I don't believe in the singularity, because the singularity violates all the other laws of physics that we know. It violates conservation of energy. It violates conservation of baryon and lepton number.
Sure.
Okay.
That's a good segue to talk about wormholes,
Yeah.
where most assuredly there's no singularity, but you can just
One
sail right
moment.
through the wormhole.
One moment, let me just mention one last remark that we all know very well. The only thing that we know about the singularity is that we don't understand what's going on there. We don't have any theory that can describe the singularity. We know that all of our theories fail at the singularity.
So why do people say that the matter is destroyed at the singularity? Physicists believe this.
This is according to a failing
I don't
theory.
think anyone does, really.
This is according to our failing theories. You know that our theories are failing there.
And they believe that a black hole, the interior of a black hole, is empty space. I don't believe that you can fall into a black hole. I believe a black hole is solid.
Well, well, you know, we'll have to see about that. I'm gonna take.
We are waiting for your screen.
Yeah, let's see here. So I'm gonna start with. Can you see my screen?
No.
Oh. Doo-doo. How about now?
No?
Really?
Let me see if I can unshare.
Oh wait, no,
my-
I got it. Okay.
Ah, yeah, now we see you.
Okay, cool.
Perfect.
So, gonna give like a brief review of what we talked about last time. And in fact, I like rewrote some of the notes, I think, in a slightly clearer way. We began by talking about fermion oscillators. Here's their commutation relations. You know, unlike the bosonic oscillators, they involve the anti-commutator. We can represent like the individual creation and annihilation operators with these little 2x2 matrices. Except we have to have this relation that when we swap the order of the creation of the fermions, we have to pick up a negative sign. And so we can actually use Pauli Z matrices to implement those commutation relations. And so we do something like this. Here's some code that I'm going very quickly through this just because we talked about it last time. Just stop me if there's any, you know, questions or concerns. This code just implements this. So tensors up the creation and annihilation operators with appropriate identities on the one hand, Z's on the other hand, and then tests that the commutation relations are there. And it worked. Now, we then discussed how you can take like a normal fermion and you can split it into two Majorana fermions. And the idea is that a Majorana fermion is its own antiparticle, which concretely means that its creation and annihilation operators are the same operator. So metaphorically, you could think about them like the square roots of normal fermions. And you know, it also means that like if you're like in the vacuum state and you apply a fermion operator and then apply it again, you're back to the vacuum state because the operators cancel out because the creation and annihilation operators are the same operator. At the same time, we're justified in calling them fermions because if we have two Majorana operators and we swap their order, we're going to pick up a negative sign, just like with a normal fermion. Given normal fermion creation and annihilation operators, we can form we can split that fermion into two Majoranas using this relation. So we'll call the one Majorana left one, and the other Majorana the right one. And so we take a single fermionic mode, we add up the creation and annihilation operators, we get the one Majorana, and we subtract and multiply it by I, get the other Majorana. And unlike the normal fermion creation and annihilation operators, these operators are actually Hermitian. If we take a bunch of normal fermions, split them into Majoranas, then those Majoranas will satisfy this relationship here, which is a little different than the one. When I rewrote this, I changed some of the normalization conventions, so be aware of that if you happen to notice it. So, you know, this code right here splits a fermion into two Majoranas. So you can see it's just a direct translation of this statement into code. And this function tests that these operators we get, in fact, you know, have this relationship with the anti-commutator. And so we can test it out. Just make sure that the commutation relationships are satisfied. Here we test that, you know, the swapping the order of applying the two Majorana operators and multiplying by -1 gives the same thing. So here we have like Majorana 1 on the vacuum, Majorana 2 on the vacuum. It's just the same as Majorana 2 followed by Majorana 1 with a negative sign. And then furthermore, that applying a Majorana operator twice is like doing nothing at all. It's its own antiparticle. So, you know, we've seen like in the case of qubits, strings of Pauli operators form a basis, which is cool. And something analogous works here with the Majoranas. If we take n Majorana operators, we can consider combinations of them up to some length n, and those operators will form a basis. So, you know, if we had, if we had 3 Majoranas, you know, we could take this set of operators, 0, 1, and 2, 0, 1, 0, 2, 1, 2, and 0, 1, 2, etc. And we can express any operator as a linear combination of those. And then we can, so here is some code. This constructs the Majorana basis. Note that there's like this little normalization that we use for various good reasons. You know, we just basically go over the different combinations of length n of the different Majoranas, and we multiply them all together, normalize it. This is a little function that takes an operator and takes the inner product with each of the Majoranas and gives us a coefficient for each of them. And this is a function that takes a bunch of coefficients, multiplies them by the corresponding operator, sums it. And so we can combine these two and check that this works. In other words, we can construct this Majorana basis. We can generate a random operator. We can expand the operator in the Majorana basis. And then we can go in reverse and like recover the original operator by multiplying each of those coefficients by each of the operators in the Majorana basis. We can compare that we get exactly the same operator. Now, just as we can take a normal fermion and split it into 2 Majoranas, we can also take any 2 Majoranas and fuse them into a normal fermion. And in a way, this is sort of quite analogous to what we talked about when we were talking about Bogoliubov transformations and so forth. It's sort of like a fancy way of, you know, rearranging, you know, what we consider to be a particle, and then we can explore the relationship between, say, the different vacuum states that are associated with these different sets of fermions. And we'll see that that's sort of how we're going to implement our two entangled black holes that we're going to, you know, have a traversable wormhole between. So if we have 2 Majoranas, call them left and right, we can, you know, run the equation in reverse and get a normal fermionic creation and annihilation operator by just taking these linear combinations of 2 Majoranas. Add up left Majorana plus I times the right Majorana, and, you know, left Majorana minus I times the right Majorana.
Can I ask a question, Matt?
Sure.
You know, there are right-handed and left-handed electrons.
Yeah, nothing to do with that. I just...
It has nothing to do with that. So
yeah,
this is just a mathematical decomposition.
Well,
Essentially.
you could call it, you know, the one Majorana A, Majorana B. I just chose to name it that.
But I mean, does this relate to real particles? I believe I've read that neutrinos could possibly be Majorana fermions.
I have no opinion about that.
You know?
Majorana fermions, yeah, I mean, you know, come up in many different kinds of contexts.
But is there a belief that they could exist, or is it just a mathematical decomposition? That's what I'm trying to understand.
Yeah, so far as I understand, yeah, like in different condensed matter systems, you know, you can basically find, you know, the fermionic systems, and you have Majoranas that propagate sort of like on their own. You'll see what we're going to be using them for shortly in this context. So let me draw this out. So suppose we start off with 2n normal fermions. We're going to have n fermions on the left and n fermions on the right. So if you remember what we talked about last time, this is actually going to be kind of the reverse of what we did last time, because I think this is going to be easier to see. So we'll call this the left side and this is the right side. Again, that's, you know, just convention. Like one's gonna be like basically end up being like the left black hole, and one's gonna be the right black hole. So, you know, suppose we have two normal fermions on both sides. So we can obviously split each of these into Majorana's. So we take each fermion and split them into two Majorana's. So we end up with 4 Majorana's on the one side and 4 Majorana's on the other side. And I'm realizing that you probably can't even see that. Can you see my my board here?
Very small. It is.
Oh, it's
Yeah,
small.
it's hard to see.
Okay, how about now?
Looks like a genealogy chart.
That's it. Much better.
A lot of glare from
Yeah, there's
lights.
a lot of glare. Yeah, let me turn off the lights.
Ooh, that's worse. You
Dark.
need ambient light somehow.
That's so true. Yeah, I have one other light.
Think that's worse? At least we can read the Greek letters with the light dimmed.
Yeah, maybe I'll put like, here, I'll put my phone. Yeah, look at that. That's nice. Okay,
That's okay.
I got it.
Yeah,
My
better.
phone flashlight here was what it calls a shadow effect. But okay, so we got left side, we got right side. These are here normal fermions. Everyday normal fermions. Here we split each of the normal fermions into 2 Majorana's. And so we end up with 4 Majorana's on each side. So what we could do is this. And in fact, let me use like a different color. Let's take these two and turn them into a normal fermion. Like let's fuse these 2 Majorana's into a normal fermion. Let's take these two and get another. Let's take these two and get another. Take these two and get another. So we started out with 4 normal fermions, 2 on the left, 2 on the right. We then split these two into 4 Majorana's, 4 on the left, 4 on the right. And now what we've done is we've got 4 normal fermions, each of which is built out of 1 Majorana on the left and 1 Majorana on the right. 1 Majorana on the left, 1 Majorana on the right. And so they're like ordered in a sense, right? That like take the first Majorana on each side, get this, second Majorana, third Majorana, fourth Majorana. And so the question is, what's going to be the relationship between the vacuum states of these fermions and these fermions? And the punchline of this part of the story is that if you look at these guys, which we're going to call, and this is like a little bit different terminology or use of terminology than last time, we're going to call these the complex fermions. And the point is that the vacuum state, the state of 0 excitations of these guys, is going to be a maximally entangled state between left and right of these guys. Okay, so there you go. There's that.
Hey, Matt, is there any operational equivalent of the mathematics that you just described? You described the formal procedure where you split the fermions into Majorana pairs, then you combine Majoranas into complex fermions. Is this something that is a corresponding operation in the laboratory?
You know, this, in a sense, operation, yeah, can be realized. I mean, I can't give, I don't know, like I can't give a more specific answer than to say, well, we're about to see how something like this can be realized in this
Okay.
wormhole like construction, basically. You know, I can, as I learn more, you know, I'll let you know if I have more interesting examples than that. So you can see here, I've just written it out. You know, if you had two fermions on the left, two on the right, you could take these combinations and then get these complex fermions. This is just basically what I just said. So we can actually do it. Here's a little code that joins two Majoranas into a normal fermion. And again, when I say join, you know, in some sense, it's like a mathematical device, like a way of translating between, you know, two different kinds of vacuum states. And so in that sense, it's not unlike, you know, these Bogoliubov transformations we were talking about before, but just sort of reformulated in a different way. So what we do here is, you know, we create fermions, the left and right fermions. We create the left Majoranas, create the right Majoranas by splitting those fermions, and then we join up the fermions, one on the left, one on the right. And then we're going to test whether those, A, the original fermions have the right fermionic commutation relations, B, do all those Majoranas satisfy the Majorana commutation relations, and C, do the complex fermions that we get also satisfy the normal fermionic commutation relation. So sanity check, let's just make sure everything works. Then we're going to construct the number operator, the total number operator of the left and right fermions, and then the total number operator of the complex fermions. And then we're going to compare, on the one hand, the left-right vacuum, which in this formulation is just the usual vacuum basis state, 1, 0, 0, 0, 0, or whatever. And then we're going to compare that to the vacuum state of the complex fermion total number operator. And we're going to look and see, you know, so for example, here's the output, right? Okay, the commutation relations were satisfied. We can see that if we take look at the total number expectation value of the left-right number operator on the left-right vacuum, naturally it's 0. Similarly, the complex number expectation value on the complex vacuum is 0. But, you know, the complex number operator on the left-right vacuum and the left-right total number operator on the complex vacuum are not 0. In other words, and in fact, they're both the same number. They're both 4. And in fact, 4 is the number of fermions that we started with. 4 in the simulation, not on this image that I drew here. The way that the simulation goes is there's 4 fermions on the left, 4 fermions on the right, and then you get, you know, 8 Majoranas on one side, 8 Majoranas on the other side, whatever. Anyway, you may have noticed that this is like the reverse of what we did last time. So in other words, last time, the way I wrote the code was actually that the basis that we worked in was one in which the complex number operator was diagonal. Whereas this time I'm working in a basis where the left-right total number operator is diagonal. And so it's, you know, physically the same thing. The benefit of doing it this way is that since we're working basically innately with the left-right vacuum, basically, we can easily take partial trace of the left side and the right side. And doing that, we can confirm that if we're in the complex fermion vacuum, the left side and the right side are maximally entangled. So here we take the partial trace, left side, right side, and calculate the von Neumann entropy. And we see that it's equal, in fact, to the maximum possible von Neumann entropy. So, we mentioned last time, you know, all that we got sort of really into this idea of like, you know, if you have a in the string diagram, you have a cup or a maximally entangled state, and you act with some operator O on the left, it's actually completely equivalent to acting with the transpose of that operator on the right. That's just true in life, like when you're working in the computational basis. And, you know, the beauty of the string diagrams is that you could just see that if we just swing this operator around the bend, it's going to be upside down. And we denote that with the transpose. Now, actually, in this case, when we're working with these Majoranas, we don't actually take the transpose. It suffices simply to multiply all the right Majoranas by negative I. So this interesting way, we can, in this formalism, we can sort of trade, in a way, a 90-degree rotation of the matrix for a 90-degree rotation in the complex plane. What do I mean? So if we take an operator, O, here's just a random unitary operator that acts on like one side, like in the dimensionality of one side here. So 2 to the little n, which is 4. We can get its Majorana coefficients, right? So I expand that operator in the basis of strings of Majoranas. Furthermore, like I have these left Majoranas and these right Majoranas. I construct a basis that's built out of like only the Majoranas on the left and a Majorana basis built out of the Majoranas on the right, all multiplied by negative I. Now, there are, so what I can then do is I have these coefficients for this operator, and I can then upgrade that operator into an operator that acts only on the left, that's like built out of the left Majoranas, by just multiplying the coefficients by all those strings of Majoranas built on, coming on the left. And I can do the same thing with these, with this right Majorana basis. And you can see that acting on the left on the complex fermion vacuum is the same as acting on the right on the complex fermion vacuum, where, you know, even as OL and OR are not equal. In other words, OL is this operator acting on the left, OR is the same operator acting on the right, except we've taken all the Majoranas and multiplied them by negative I. So like in normal like world, this should be something like, you know, operator acting on the left on the vacuum is this, on like an entangled state, is the same as the operator, the transpose of the operator acting on the right. Like this is just supposed to be this equation. Operator on the left, same as transpose of operator on the right. We can see in Majorana world, that's true if we just take the Majoranas and multiply them all by negative I. So now we turn to discussing the size operator. This is a very cool part of this whole formalism. So if we act on the left with some operator, so we have an operator built out of left Majoranas, and we act on the complex fermion vacuum, which again is a maximally entangled state between left and right, then if we look at the expectation value of the complex fermion number operator, the total number operator, it's going to give us the size of the operator that we acted with on the left. In other words, the number of Majorana fermions that are in that operator. What do I mean? So here is this little function. what we do is we take an operator that acts on, like in the dimensionality of like half the size of this system. We expand it in terms of Majoranas, and then we build it out of left Majoranas, and we act on this complex fermion vacuum state, which is maximally entangled between left and right. And then we take the expectation value of the total complex fermion number operator. So what does that give us? If we, oh shit. Gotta run all the cells, okay. So we can be like, all right, we have just Majorana operator 0. It's just numbered, right? M0, Majorana operator 0. What's the size of that? Oh, it's 1. That makes sense. What's the size of Majorana 0 times Majorana 1? Oh, it's 2. There's 2 of them multiplied together. What's the size of this one? Majorana 0 times Majorana 1 times Majorana 2. It's 3. Furthermore, we can drill down, and the individual number operators corresponding to the individual complex fermions count the number of like individual Majoranas. So for example, given this multiplication of 3 Majoranas, I can be like, you know, what's the expectation value of complex fermion number operator 0? And it's 1 because there's 1 Majorana 0 in this operator. Similarly, there's 1 Majorana 1 and there's 1 Majorana 2, but hey, there's no Majorana 3s. And so we have this sort of like beautiful formalism where literally the size, so to speak, of an operator is given itself by an operator. Like literally the expectation value of this operator is going to be a measure of, in some sense, the complexity of the operator. How many Majorana fermions go into making this operator up? And so we'll see how that will manifest in the wormhole context very shortly. So next we have to introduce our dynamics. We have the SYK Hamiltonian. We generate a bunch of little, you know, coefficients, C, I, J, K, L. We take a bunch of Majoranas and we group them into groups of 4. And we have a little weight on that. So in other words, for a choice of C's, which, you know, are like randomly chosen, like normally distributed, we basically get a 4-way interaction between Majorana fermions. This is the famous SYK model. And people like it because it's highly scrambling. If you've read the wormhole paper, you know, it'll tell you that in the limit of many, many Majoranas, it demonstrates so-called perfect size winding. We're going to come back to that later. And it's for that reason that people use it.
Matt,
Mm-hmm.
if all the Majoranas are identical, does this mean that all the C's will have the same value?
They're, well, what do you mean? So each Majorana is a separate operator.
It's a separate operator, but they all correspond to electrons. Let's say, if I'm not talking about Majoranas, are they all electrons? Are they all protons? Or can one be an electron? One can be a proton. One can be a neutrino.
So, you know, the term that they use is like, these are like different, you know, flavors of Majoranas.
Yeah, yeah.
So, you know, like in these systems we've been working with here, you know, it's like there's ultimately, you know, what is it? 8 Majoranas on the left, 8 Majoranas on the right, and each is built out of, you know, these normal fermions. So, I mean, like we're not even, you know.
Okay, let me go back. Suppose that the normal fermion you started with are all identical fermions. Does this mean that all the Majoranas will have the same flavor?
No. you know, like, and in fact, like, we're not even considering, you know, like the single particle wave functions of like any of these things, right? Like, we're just working with, you know, a bunch of different fermionic oscillators that are tensored together. The reason that we think these people like this SYK model, as I say, is it's highly scrambling. And therefore, you know, because we also think that wormholes, black holes as quantum systems are going to be the fastest scramblers in nature, we like the SYK wormhole because it gives us a way of sort of playing around with that idea. So when we talked about the wormhole in the qubit context way back when, the rule was we chose an energy operator for like the black hole. And you would have a left black hole and a right black hole. We have certain Hamiltonian. The idea was that the Hamiltonian on the right is the transpose of the Hamiltonian on the left. So in this context, we know what we should do. Instead of taking the transpose, we just build it out of right Majorana all multiplied by negative I, because we've seen that that's equivalent of taking the transpose in the normal computational basis. So what we do here is this generates a bunch of random, this generates like the different coefficients in this SYK Hamiltonian. This actually, you know, does the sum. We give it like the couplings between the groups of 4 Majoranas and a list of all of our Majoranas, and it goes through them 4 at a time, multiplies them all together, weights by the coefficient, and sums over the whole thing. And so we construct our SYK Hamiltonian. We can build it out of like just our Majoranas, that as many Majoranas as are on one side. So that's M here. We build it out of just Majoranas on the left. And here we build it out of just negative I times all the Majoranas on the right. So here's our left Hamiltonian and here's our right Hamiltonian. And you know, the point is it's the same SYK couplings, just built out of left and built out of right Majoranas. But with the right, we do this sort of transpose thing, but where it's not like actually taking the transpose of the matrix, but doing this funny operation with the Majoranas, a little complex rotation instead. And we can see that just as before, we get this sort of relationship. So if we take our operator on the left and our operator on the right, we can evolve them in time. So OL is this function evolves this operator, like in the Heisenberg picture, in time under the left Hamiltonian. And this takes the operator on the right and evolves it in time using the right Hamiltonian. And we can see that operating on the left in the past is equivalent to acting with the operator on the right in the future. Get exactly the same state.
Where do you see the past and the future?
So I evolve OL. So remember, OL is here, this operator, which is built out of only left Majoranas. OR is operator built only out of right Majoranas, each multiplied by negative I. And this is just like the Heisenberg evolution of the operator. So given some t, we evolve it backwards in time by t. So this evolves OL backwards in time, you know, to like negative t equals negative 10. And this one evolves it forward in time to t equals 10. And their action on the complex fermion vacuum, which again is this maximally entangled state between left and right, gives you exactly the same state. And again, it works because we're dealing with a maximally entangled state between left and right. This will only work if we have a maximally entangled state between left and right, as we'll see. Because what we're about to talk about is, that's completely unrealistic. So what we actually want to use is not this complex fermion vacuum maximally entangled between left and right, but instead the famous thermofield double state. The thermofield double state at infinite temperature is just the state we've been using, maximally entangled between left and right. But the idea is that at finite temperature, it's, less entangled basically. And so it it mostly works, but not perfectly, like you see here. So,
what is TFD?
right. So so one way, the famous way of looking at it is this basically, right? So you take some Hamiltonian and you that's fine. You basically create an entangled state where it's like a sum over all of the different energy eigenstates, each weighted by something that has to do with the energy eigenvalue. So the point is that
What are N1 and N2?
those are the energy eigenvectors.
So those are two eigenvectors corresponding to En. Both of them correspond to the same En.
Yes, exactly. Now, actually, let me open up they had a more, a better way of writing it out. In the wormhole paper, here we go. Okay, so we see here, so we have a Hamiltonian, it's got some eigenvectors, and they are labeled by J here, J, energy levels. And we basically take the conjugate of the conjugate of, the energy eigenvector, tensor the energy eigenvector, for the same J. So for the same, it's just the same eigenvector. And we weight it by this exponential of, it has to do with the energy eigenvalue. And we sum over all that. And the point of doing this is that it's like an entangled state between left and right. But if you look at the partial trace, if you look at just the state of the left, you get a thermal density matrix. So when we think about it, this is like the purification of the thermal density matrix. So the thermal density matrix is given by, you can think about it like at a given temperature or inverse temperature, which is beta. It's just basically negative beta times your Hamiltonian exponentiated and then kind of normalized. And the idea is that the TFD is a entangled state, generally speaking. You'll see that it's at infinite temperature, when beta is 0, it's maximally entangled between left and right. And as you lower the temperature, it gets less entangled. But either way, when you partial trace over both sides, you get the thermal density matrix back as the partial mixed state of left and right. So if you're interested in looking at the matrix elements of this, we can see it, but let's just choose beta to be 1. We construct the thermal density matrix, construct the thermofield double state, and indeed the partial state of the left is equal to rho, and the partial state of the right is also equal to rho, rho being the thermal density matrix. Now, one cool thing about this is we can now get a temperature dependent notion of size. quite simply. In other words, instead of evaluating the size of an operator by like, acting with the operator on the left and then getting the expectation value of the complex fermion, complex fermion number operator on the maximally entangled left-right state, we ask after its expectation value on the thermofield double state. And so it's going to depend on temperature. And so here it's just the same code from before, but you see it's like a little bit, it's just a little, it's just like a little different, I'm saying? Like instead of this being 1, it's like 0.98. And, if we adjust the temperature, if we keep cooling it down, these numbers are going to get ever more, different than the size at the infinite temperature, in the infinite temperature state, which again is the maximally entangled state. So again, yeah, infinite temperature is a complete idealization. So, and indeed, it's like no matter what dynamics we choose, the infinite temperature state it's just the maximally entangled state. But, at lower temperatures, like the thermofield double state, like depends in a non-trivial way on like which dynamics that you chose. So, stuff's coalescing here. I mean, we got, we got left side, we got a right side, we got some Majorana fermions on the left, got some Majorana fermions on the right, size operator, got thermofield double state. Okay. But we want to make a wormhole, and we want to be able to like throw a qubit into this wormhole and have it pop out the other side. And so the question is, how do we work with the qubit in this context? So when we did the qubit-based like wormhole, that was like pretty trivial in a way, right? We had like some qubits on the left, some qubits on the right, and we had some like qubit that we wanted to send through the wormhole, and we actually just used a swap operator. So we just sort of swapped in the one qubit. It's like there was like, one black hole on the edge of, one qubit on the edge of the left side of the black hole, and we just swapped it with this qubit that we wanted to be the message. And then it got scrambled over, and then we coupled the two sides, and then evolved the other side, and then that original qubit reappears on the right. But what do we do here? All we have are these fermions, normal fermions, complex fermions, Majorana fermions. How can we deal with a qubit? And there's a beautiful, elegant way of like dealing with this, because it turns out, this is great, I love this. It turns out that just as we can take two Majoranas and form them into a complex fermion, if we take 3 Majoranas, we can build a qubit out of them. So if we take, let's take 3 Majorana operators, call them psi x, psi y, and psi z. If we take this, if we do these expressions, negative I times psi x, psi z, negative I psi z, psi y, negative I psi y, psi x, those operators we get satisfy exactly the same commutation relations as the Pauli matrices. And so you're like, fuck yeah, we can just build qubits out of Majoranas. So here's some code that, takes 3 Majorana operators and builds a qubit out of them. This is some code that tests that, in fact, we have the right commutation relationships between Pauli x, y, and z. And this just, is a classic, like, let's evaluate the expectation value of x, y, z on some state. And what we're going to do is we're going to build a qubit out of the first 3 Majoranas on the left, and we're going to build a qubit out of the first 3 Majoranas on the right. And we test that, in fact, they follow the right relationships for the Pauli matrices, and they do. So we're almost done. We're like, this is the climax is coming. It's coming. Got just almost there. So so what we're gonna do now is we need a message, just like an actual qubit to send, and we're just gonna send a qubit in the Z upstate, just for simplicity. We can change this around if you're interested. So we tensor that qubit with the thermofield double state. So we got this qubit that's sitting outside. We got this left black hole. We got the right black hole. We then have, you know, the Pauli matrices that act just on that message qubit. But we still have to actually swap the message qubit into the wormhole. Like, we need to like we have this qubit that's sitting outside, and then we have this qubit that's built out of the first 3 Majoranas on the left. And we need some way of swapping them, okay? So how are we gonna construct a swap operator? And it's not difficult. All we need to do is use our friend, like the Pauli basis, like just like we were alluding to, similarly to the, now the analogy works reverse. Just so we can break an operator down into strings of Majoranas, we can break a operator down into strings of Paulis. So what we can do is we can take our normal swap operator and we can expand it in the Pauli basis. So we can write it as a linear combination of Paulis. And here, let me just evaluate these cells, and then I'll show you what it is. It's actually like not even that. Yeah, like if you expand the swap operator in the Pauli basis, you find that it's just I tensor I, plus X tensor X, plus Y tensor Y, plus Z tensor Z, all multiplied by 1/2. That's just another way of expressing the swap operator. So then it's quite obvious what to do, right? Because we have XYZ operators that act on our message qubit. We have XYZ operators that act on our qubit that's built out of the first 3 Majoranas on the left side. And we just, build a swap operator out of those two. So that's what this does. And we can see that it works. So again, we started with Pauli, we started with Z up being the state of our message. And we check, here's the XYZ expectation values of the message qubit and the qubit on the left before we do the swap. And indeed, it's just up in the Z direction, and this is just 0, 0, 0, maximally mixed state, whatever, who cares? After the swap, boom, hell yeah, they just switched places. And we can swap again, swap it back. So yes, our swap operator really works. Awesome. So now we have all of the ingredients in place. So you can see this is like the very end of it. Let's actually send the qubit through the wormhole. So we just have to take our left Hamiltonian and our right Hamiltonian, make sure we tensor them with 2x2 identity, because we like added this message qubit. And the big thing, and I guess next time we can talk more about like the theory of this, but we had to choose in our wormhole, what's the coupling between the left and the right. Like if we recall, we look here at the diagram here, we got our thermofield double state, we got the left, got the right. What we have to do is evolve the left backwards in time, insert our message with a swap, evolve the left forward in time, and then we got to couple left and right. And then after that, evolve the right forward in time, and then our qubit's going to pop out. But what was this coupling supposed to be? And in the qubit case, we used a ZZ coupling. But the awesome thing, and this was one of the motivations for bringing up the whole size operator business, is that the coupling that we need, that is the right coupling, is just the size operator. And in fact, though, we don't use the full size operator here because that would be like cheating. We actually use the size operator built out of all but, or like excluding the first 2 complex fermions. Why? Because it would be cheating to like include our message qubit, or like the, we got the message qubit, and then we have like the qubit built out of the first 3 Majoranas on the left, and then the qubit built out of the first 3 Myron is on the right. So when we think about the complex fermions, these are going to be built out of the first 2 complex fermions. So we want to like exclude those from the coupling, because otherwise I would be cheating. Okay, so that's what why that 2 is there. So here is basically a function that like does the wormhole thing. So given a state, like the thermofield double state plus the message, what this does, we start with the state, we evolve the left, backwards in time, insert the message, evolve the left forward in time, do the coupling, and then evolve the right forward in time. And we have to do a variation on this parameter G. In other words, the whole thing here is like, yes, we've determined like what the coupling should be at the level of the operator, but what's the strength of the coupling gonna be? And so what we're gonna do is we're gonna iterate over like, what are a bunch of different possible values for this G, evaluate this for each value of G, and we're gonna choose the value of G that maximizes the expectation value of the Z operator. Why? Because we started out like in the Z up state. And so we want to choose a G that gives us, you know, as much as we can, that the qubit on the right is going to be in the Z up state. So we run this. So again, you know, there's the wormhole. So we just, you know, it's all the possible G's. We iterate over the G's, evaluate the wormhole with that G, take the expectation value of the qubit on the right, like the output qubit, evaluate the expectation value of the Z operator, and then take the G that gives us the largest value of the expectation value of Z. And that's going to give us, you know, once we've determined what that G is, we like are like, yo, what is, you know, let's evaluate the wormhole again, you know, given that G value just to get the final state. And then like, tell me what this qubit coming out of the right ends up being. And, you know, the way we've set it up, it's not going to be perfect. I mean, we're only using like 4 fermions on the left, 4 fermions on the right. So, you know, 8 Myron is on the left, 8 Myrons on the right, 16 Myron is total. It's not much, right? So, like, our expectations are low. But it actually works pretty well in the sense that the qubit that pops out is like, okay, negative 0.02 in the X, negative 0.03 in Y, but like 0.5 in Z. Like, that's pretty fucking good, actually, all things considered. And here we see a plot for like the different values of G, the expectation value of like the Z operator. And we can see that, you know, here is a little, you know, like here's like the peak basically. And in general, this is going to be like a symmetric looking. Unless you think that this is like just some hand waving, you know, let's just try it. Let's send a qubit that's pointed in the X direction instead. You know, why not? So let's send an X qubit. We see here, oh, X direction, swap it in. Okay, that all works. That's all the same. And then we just got to change this here. We got to instead evaluate the X, you know, operator. And it'll chug away. Takes a second. Like even with this small number, takes a moment. Takes a moment to, oh shit, there's a little typo though. Put X there. In any case, yeah, while we wait for that to do its thing.
Why isn't it symmetrical? I noticed it's almost symmetrical.
Yes, good question. Yeah, it's not perfectly symmetrical because I've discretized G. In other words, I only choose 50 slices between -5 and 5. And so it's just,
yeah,
you know.
Oh, yeah, this is similar.
Yeah, it looks, yeah, basically symmetrical. And here, yeah, look, Z is like 0.04, 0.04, Y is negative 0.02. But hey, there you go, X. Not too shabby, And in some ways it's more interesting, right? Because like, if the qubit was transmitted perfectly through the wormhole, like what would that imply? It would imply that as it sailed through the wormhole, it just experienced like empty space, nice smooth space, not curved, like no interactions. Like that's nice for the qubit, but pretty boring, right? The fact that this qubit got all fucked up, like when it was going through the wormhole, means it encountered some interesting stuff like on its way. And so, you might wonder, could you kind of try to diagnose what the interior of the wormhole looks like from, studying what happens to these things that, we study?
What you're saying, though, this is mathematics, and this isn't real physics. I mean, it's not really happening. There isn't really any disturbance in the black hole. But I don't. Well, okay. I don't like that explanation. Put it that way. Why it's not symmetrical? I guess it's just it's yeah.
Oh, sorry, I misunderstood you. Yeah, I mean. Or wait, say it again?
No, I'm saying that all this is very mathematical. I mean, okay, I still don't understand why it's not symmetrical. But your explanation didn't explain anything to me. That is, if there's any disturbance like a noise or something like that got into the system, I would like to see that shown in the formula. Here we added noise and its randomness. Was there randomness added?
Oh, I see what you're saying. So, okay. So like, first of all, so we generated like a random Hamiltonian of the SYK form.
Uh-huh.
So, people have shown that like in the limit where you have many, many, many fermions, and you have an SYK type Hamiltonian, that it'll work perfectly.
I'm starting to realize that this was like only the first few terms of an infinite expansion.
Yeah, that's a good way of thinking about it. Yeah, so like they've proven that like in the limit of like many Majorana fermions, these qubits can get across basically.
Okay, and there's no infinite temperature or anything like that.
Yeah, exactly. Well, so yeah, in the end, I ended up not doing it at infinite temperature. So
yeah,
temperature 1 or whatever.
Okay.
So we could do it at even colder temperatures, and you'll see it'll just like work less well. You know what I mean? So yeah, for this general class of dynamics in these certain limits, you can show it works perfectly. In this case, as I say, we just have a handful of fermions, and there's no reason really to expect that it's going to work perfectly.
Mm-hmm.
But again, you look at this thing, and what's what's happening? It's like we start off with this entangled state. We throw this thing into the wormhole, into the left black hole, and it gets rapidly scrambled over all of the degrees of freedom on the left. And then the left and the right are coupled, like for moral reasons, not including those fermions that were used to encode the message. We get this coupling, and then we do the reverse, kind of like a sort of unscrambling on the right. And again, considering the analogy to quantum teleportation, we can think of this as being like our cup state, and we can think of this e to the IGV as being like, in the teleportation, like measure the left, record the results, send the classical bits to the right, do a unitary correction. So actually, you can reformulate this wormhole construction to make it like even more analogous to teleportation, in the sense of like, instead of doing this sort of coupling like this, instead you could just measure all this stuff on the left and then send some classical information over to the right and do a unitary correction. And then it would be like exactly analogous to teleportation, because you'd have to admit, so that's what I want to point out. This e to the IGV, like think of it like a classical coupling, like not a quantum coupling. Like this makes you think like, oh yeah, like maybe that qubit's kind of just like, you know, moving to the right over here, like through this coupling or whatever. But it's not. It's actually going through like the entanglement, right? Like in exactly the same way as in teleportation. I can rewrite this as like a measurement on the left and then a classical transmission of information controlling a unitary correction on the right. And in that case, you know, just as in the teleportation example, it's like the only way that this, you know, like in the sense that quantum information is being transferred, it's being transferred through the entanglement. And so the idea is that in this case, this entanglement in the thermofield double state has the interpretation of being a wormhole. So, I mean, the moral of this paper, right, is when they say quantum gravity in the lab, is that, you know, barring actually making black holes, we can study systems, condensed matter systems, different kinds of systems that have this mathematical form. And so would like demonstrate this kind of phenomenon. And so we can try to like understand it better. So like in this paper, you know, we just went over, so, you know, before I guess we talked about the qubit case, and, you know, now we talked about this SYK case. But here, you know, it's like they talk about like, hey, you know, the Hamiltonian for a Rydberg atom array is like pretty scrambling. Like maybe you could use that. And they did some experiments with that. Or like, maybe we could, you know, do it with trapped ions or, you know, different things like that. So, you know, to the extent that like, yes, you know, what I've shown you here is like, in some sense, I mean, this is like a concrete model in the sense, like if you could like realize this like SYK, you know, coupling in the lab somehow or some way, you know, whatever, you could do that. But, you know, the point perhaps is like, this is the general form of a wormhole. What we mean by like general class of things called wormholes in the context of quantum mechanics, right? Like this is definitely nothing that you could ever derive from general relativity. So, you know, next time, I know I realize that I, you know, zoomed my way through this. We can, you know, go over some of these steps in slightly more leisurely detail next time. I can show, like I have this sort of like an animated version, and we can talk a little bit more about like the theory of like size winding and you know, like why, like a little bit better, like why this should work. I may as well I mean, if you guys are still have, you know, a couple more minutes, I can show you this. It's not even that interesting actually, but it's worth looking at. SYK. Yeah, we'll talk about more of the details next time of this. So you can kind of drill down and like more and like think about, you know, the different operators that correspond to like geometrical notions involving the wormhole. So, you know, like a boost operator, momentum operators, and like stuff like that. And you can think about how they're related to the operators that we've defined already, like the size operator, the Hamiltonian on the left, and whatever. So, yeah, you know, what I got here is, you can see, all right, like these are the expectation values of the left fermions. These are expectation values of the right fermions. We're in this, well, you wouldn't know it's the maximally entangled state between left and right, but it is. And you know, you see that's got like expectation value of 0.5. And then we got, here are the expectation values of the complex fermions. And we see they're pretty low. And then here, this is our, you know, qubit on the left, and this is our qubit on the right. Red is left, blue is right. We've optimized our wormhole. You know, we've chosen some value of Z. I believe I have it that we are working with the initial state being in the X direction. So then I can like, oh. Shit. Hello. My keyboard's not working. Sometimes that happens. Ah, shit. Gotta start it over. Anyway, it sort of like animates, like, okay, so like insert the qubit, and then we can, you know, watch what it looks like as it evolves. So this is like a little bit more of like a more continuous notion of what's happening. So like instead of like evolve on the left, like, or evolve backwards on the left, insert it in, evolve forward, couple, like evolve on the right, you could sort of like imagine that all kind of bundled up into one type of evolution that's just sort of continuously happening. Again, like that's more like, we can talk about that in more detail next time. But for example, we can, you know, insert the qubit, and then boom, okay. You see here, we now have that, we've sort of swapped in the qubit that was in the X plus direction. And so now we see that here in red. And, you know, we can look and be like, oh my God, look, the expectation values of the complex fermions are different, okay. And then we can evolve it. And just kind of look at it. I mean, ay, ay, ay. Okay, well, I did that quite, sorry. I put in a very slow value, or a very, it's evolving very slowly. I should have chosen a higher number. Let's do that. Okay, so you can start to see that this guy's shrinking. Okay, okay. Something's happening down here. It's getting scrambled, something's going on. So that's disappearing its way into the maximally mixed state. But low, something you sort of see something happening over there on the right. What's going on over there? Something starteth to appear. Hard to see, very tiny. Sorry, it's quite slow. Apologize. Speed it up. Just go crazy. Yeah. Still pretty slow. Anyway, this is the part that this is why I hesitated to show it now. I still got to do a little bit more work to like, I want to do it. So like when I press the button, like, and it just automatically evolves it in time to the right place that you want to look at. Yeah, you saw a little spike there, of course, pointed in the opposite direction. Oh, boom, there we go, look at that. There it is, coming out, popping out on the right. And you can see it kind of now is sort of oscillating back and forth. So, visualization, maybe that helped, I don't know, in some way. Let's just do it again. Optimizing. And yeah, I put links to many of the things that we talked about last time. So, you know, here's a link to the Quantum Gravity in the Lab paper. This paper, Quantum Epidemiology, was nice. This one will go into a bit about like the size operator, and they call them two-sided like wave functions. This idea of like taking an operator acting on the maximally entangled state on the one side, and then getting the sort of state, left-right state that corresponds to the operator. And they go into, the Majorana stuff, complex fermions. So you can sort of compare this exposition to mine. And they go into some more detail about like, just different ways of like quantifying things like how operators grow and whatever. And then this one, I didn't use like exactly what they say in here, but they're the ones who sort of inspired, what we were talking about with like the swapping the qubits in, the qubit in with the whatever. So this is a nice reference as well. All right, just for our finale, we'll just run this one more time. Insert. Okay, there it goes. Inserted. Evolve. And then at some point it's gonna worm its way over. Yeah, like right there, that's pretty good. About as good as we got before. Again, if it was perfect, I mean, you can see it's probably like, that's the interesting thing, right? Like insofar as it's not perfect, there's going to be glitches in the direction it's pointing in. But also like kind of more interestingly, it's going to like be entangled now with stuff like in the black hole. So if it worked perfectly, it would end up, exactly in the state that it went in. And be separable, like it was separable when it went in, but we see that here. I would say that, like these visualizations are nice, but I think this gives you a clearer idea. You can see that certainly, this went in the 1, 0, 0 state, and, like this is clearly weighted towards that. These are like much, much less than this, by an order of magnitude. We can just see exactly what are the right values of G to get, nice transmission. I mainly did this visualization thing insofar as you can, so like in theory, you got these different operators that you can use to evolve it, like not just the, the Hamiltonian, but like also operators that are supposed to correspond to like a momentum operator, which in theory should just sort of translate back and forth between the left side. And so I just wanted to see what that would like look like or whatever, sort of hard to get an intuition for it. So that's what that is. But yeah, next time, we can talk more about intuitions about, why this should work, what is perfect size winding, and yeah, maybe a little bit more about like, the geometry of this. Like I know Moshe was asking me last time, like, what's this negative energy? How are we supposed to be thinking about this geometry and stuff like that? So I'll try to say at least something more about that.
Matt, 2 more questions.
Mm-hmm.
When we had the discussion about teleportation, you presented this using some very concrete items like CNOT gates and Hadamard gates. It would be nice if you could tie all these to concrete things like CNOT gates and Hadamard gates and so on. If possible, I don't know if it would make any sense.
Yeah, well, I mean, that's what we did, originally, right? So like, way back in the early days,
Yeah,
Mhm.
that's
of
what,
these.
yeah, that's what I mean. Exactly, but at this point, I do not see it anymore.
What do you mean see it? Like in the, like, I mean, we could like do a review of it. I mean, again, you can read over the notes here, you know, they're
Yeah.
all on this site. So, I mean, this is, you know, in these, you know, 7 or so
When-
notebooks,
when you talk about the Majorana fermions and so on, and evolving them, what are the physical constructs that are being used here with the Majorana fermions?
yeah, I mean, I don't have enough, you know, background in condensed matter to like know how to physically realize these, like at all. I don't know. You know, again, like in the, yeah, like in these lectures, you know, I give this sort of concrete thing that, you know, that it's just basically a sort of elaboration of this paper where, you know, it's all formulated in terms of qubits and operations on qubits. And so this time around, you know, the more traditional way, and in fact, like in a way that, yeah, the original way of talking about these things was, you know, involving the SYK wormhole and the size operator and stuff. Yeah, but yeah, as far as realizing an SYK-based wormhole thing in a lab, what would you make it out of? I'll also try to talk about that next time. Yeah, you know, I don't know really, and so I will. I'll read some papers, you know, because this is like one of the things that they work on. You know, that was like the point of doing it in a way. We want to make things in the lab that we think are governed by very similar dynamics to what we believe black holes should be governed by.
Can I follow up on that?
What makes a wormhole here? How I hear the word wormhole. I don't know what it means. I don't know how would I know a wormhole if I meet one?
So yeah, so what I would say is that, wait, yeah, Jamie says no one's done it in the lab yet. Okay, I would define a wormhole like this: 2 quantum systems that are entangled so that if something interacts with one side, and then sometime later, there is a classical coupling between the left and the right sides, then at some future time, that thing that interacted with the left side will reappear on the right side.
How does this relate to a wormhole in general relativity?
So the idea is that from, you know, like a stationary observer's perspective, a black hole could be described as a quantum system that is essentially scrambling, so that, you know, something comes into it and it seems to get scrambled out over its event horizon. And, you know, in the case of like the wormhole, then you'd have like a black hole over here, black hole over here. They're coupled by some more or less classical interaction, you know, the more realistic versions, you know, some kind of like electromagnetic field thing. And then, you know, you have the black hole on the right is also treated as a quantum system that's highly scrambling, and then the thing, you know, reappears. So again, that way of thinking about it, like, assumes, and you can disagree with this, assumes black hole complementarity. In other words, what I see as a black hole as like a quantum system, something comes kind of like starts to like get closer to it, you know, starts getting smeared out over the interior, blah, 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 blah. You know, black hole complementarity says, if you were that particle, you would experience that whole process as just falling through empty space, that you wouldn't even notice when you cross the event horizon. And in the case of where there's a wormhole, you would just sail through some interior geometry and then pop out the other side. So, you know, that's the content of the principle of black hole complementarity. So obviously in this whole discussion, we're assuming that. And we're trying to model the black hole and the wormhole
Confused
from
you.
this external perspective as quantum systems that are highly scrambling, that are entangled, and that are coupled, so that something that comes in on the left and then gets scrambled up ends up being refocused and relocalized on the right.
So can I follow up and maybe,
Relocalized, refocused on the other side. This came out very clearly when you were talking about teleportation. This I understood. Now, as far as black hole complementarity, this has nothing to do with wormholes. There are no wormholes in black hole complementarity. There are no wormholes in ADS-CFT correspondence.
Oh no, there certainly are. I mean, not in like the, I mean, you know, it's like there can be. I mean, it's sort of irrelevant, right? The black hole complementarity has to do with, on the one, you know, to say that, you know, what one person would describe as like a highly scrambling quantum system, someone else would describe as like empty space. I mean, insofar as you just take that, it doesn't say anything about wormholes. You know, the later addition is to say, if the black holes are entangled and if they're classically coupled, then the interior geometries become geometrically connected by a wormhole. And that has been investigated like in very sophisticated ways in the ADS-CFT context.
so does anybody know, maybe Jamie knows, because I know he's interested in quantum computation. Have any attempts been made to simulate this, either on a classical computer or any rudimentary quantum computer? I mean, have any of the aspects of this been tested or attempted to be tested? Does anybody know?
Which part? I mean, we've just done the classical simulation of it, so check that off our list. You know,
I mean, to give us some indication of that a wormhole might exist.
right? Like you mean like in the sense of you know,
I mean, we could simulate it
what the
mathematically.
interior would look like. You mean?
We could simulate it mathematically, even on a classical computer, but if you do it on a quantum computer, maybe some aspect of this could be confirmed, you know, some.
Yeah. Well, I did like a, you know, in the qubit model, like I did like a very shitty version that ran on IBM, or I think I used Rigetti's. I should do it.
You did run on the IBM system?
Yeah, I mean, it's not that, like, it's not that cool. Like, you know what I mean? It's just, it doesn't give you anything that you wouldn't expect, right? It's just, you have some qubits, another qubit, apply a swap operation, you know, evolve it, whatever, they're entangled. I mean, in that sense, it's no more like magical than just seeing like the Bell thing for the first time or the teleportation thing for the first time. I mean, obviously, it becomes the more impressive, the more qubits we have, and the more accurately we can transmit these things. You know what I mean? It doesn't seem to me that in the, like, if you're going to be just using a qubit-based quantum computer, like, you're going to see anything that you didn't expect to see, right? Because it's just, you have complete control over it. Like, you just have these qubits, you're just evaluating this circuit. I think more interesting is the case where, you know, you have some condensed matter system that, like, in itself is just governed by, you know, like an SYK Hamiltonian, you know, or this thing that happens to be scrambling or some other thing. And then you might actually see something you didn't expect. You know, I think that's the more like exciting thing.
I mean, you know, we have a teleportation protocol in quantum computation, but you still have to send
classical.
either classical bits to get a qubit, you know, transmitted instantaneously, or you have to send the qubit, you know, subluminally to transmit classical bits. But is there any protocol being worked on that can show that you could transmit stuff superluminally, or, you know?
Well, again, remember this e to the IGV, this, which, in our SYK model was represented by, the exponential, the size operator. This is the equivalent of that. Make a measurement, send some classical bits. So in other words, like this is a classical evolution. And instead of, representing it like in this sort of continuous circuity way, we could also represent this like with a measurement. Like in other words, I could take this operator and instead do exactly the same thing. It's like precisely to the extent that it's a classical evolution. I could make measurements on the left side and record the results, send the results to the right side, and then do some kind of like unitary correction, like in teleportation on the right side. And it would be like the equivalent of that. So again, it's not, just like in the case of teleportation, like you're exactly right. It's like, you can have two entangled black holes. Maybe there's a wormhole, some connected geometry between them. Who cares? Because it's not traversable. The thing that makes it traversable is there's going to be like some essentially classical communication, some kind of classical interaction between the mouths of the wormhole in exactly the same way as in quantum teleportation. And in fact, like that's why there's been this revolution in wormholes like these last couple of years, because people realize like, fuck, like if you can do quantum teleportation, then like you can probably do traversable wormholes too.
But it would not be superluminal. That's the point.
It would not be superluminal. Yeah, again.
Yeah.
Hell yeah.
Because, again, quantum teleportation is an unfortunate terminology because for people, the Star Trek people think that it happens instantaneously.
Yeah.
It doesn't. There's got to be a subluminal transmission, either of the qubit to transmit classical bits or vice versa.
Well, again, I mean, we talked about before the fact that, like, one can regard a kind of transmission as like taking place like at the moment that like Bob or Alice, whatever, makes her measurement on the one side. And that, yes, you have to send some bits, which takes some time, but that's
right.
Just to correct it. Now, it's a little different here in this case because, right, it's like you have these two black holes that are like whatever, separated from each other, but like they're, interacting, they're coupled in some way, but we're like throwing a qubit in on the left at some time in the past, and then at some time like in the future, it emerges on the right. And, it's supposed to be here symmetrical. In other words, like given time 0, at like negative t, you threw it in, and at positive t, it emerges. So, it's not, as far as I know, it's not like that, there's a version of the wormhole where like, you fall in the wormhole and then you're in like a time outside of time and you just like instantaneously pop out the other end. No. It's like, you're
But if the
you're
opposite,
in the wormhole for like a non-trivial amount of time.
But if the opposite ends of the wormhole are entangled, it should happen instantaneously. Or if you have two black holes that are entangled, then what goes in one should pop out the other instantaneously.
Well, again, that's what I'm saying. So there's this scrambling thing, right? So it's like you throw the guy in the left, and then after it takes some time, well, not that much time, frankly, but some time for that to get scrambled over the degrees of freedom on the left. And then similarly on the right, like after this coupling, which again takes a certain amount of time, which is what we, this parameter G, which we like had to train for. So you gotta like take into account that time. And then, you gotta unscramble it on the right? So you have this forward evolution here, which takes some time to, and there's, in one paper, I should try to find this, I don't recall exactly which one it was. They do some like quantitative analysis of like more specifically, like how long would this take? Would you really be able to get places faster than just flying in a spaceship there. Like, you know what I mean? Like the natural thing is to be like, oh, fuck yeah, wormhole, you know, shortcut, right? Like, it's,
Yeah.
is that necessarily true? And this paper talked about it. I kind of forget what they said, frankly, but I'll try to find that. But that's a little bit of a different issue than the superluminal aspect of it, if any.
Yeah. If you've ever read the science fiction Hyperion, and the ships go so fast.
Oh wait, Marty, I lost you for a second. Hello? Uh-oh. Everybody's frozen. The internet connection is unstable.
Hyperion science fiction. The astronauts that landed.
I got kicked
just-
off for a second. The internet crapped out. Wait, I'm back up.
Oh, okay.
So we're talking about Hyperion. And
Yeah, the Dan Simmons, I think his name is, the author, and the astronauts who arrived were unfortunately reduced to blobs on the floor because of the acceleration that they had to go through to go to light speed.
those tidal forces will get you.
It's not the tidal forces; it was just gravitational, G forces.
Well, material objects can never go to light speed anyway. I mean, the acceleration would have to be infinite, because as you go faster.
Oh well, yeah.
Yeah, I mean, a material object can't. But what I'm talking about is entanglement. You know, material objects can be entangled. But this whole thing with wormholes, I don't know. It just seems to be so much in conflict with what we know about quantum physics.
Oh, really? I mean, if you accept, it seems to me that if you accept quantum teleportation, it's not that much harder to accept.
No. But which quantum? We're talking about the quantum teleportation protocol.
I mean, because this is just really a generalization.
Which is limited by the speed of light.
Yeah. Well, so is this. Again, they have to be classically coupled. I think the thing that you can rightly question is the principle of black hole complementarity itself. I mean, it's a principle, it's an axiom, frankly, right? It's like, it's not been proven in any way. It's like, there's reasons for believing it. It leads to a lot of elegant ideas.
Well, Moshe disproved it. You weren't at that.
Sorry.
Okay, there are two parts to it. As far as black hole complementarity, stating that there is a membrane enveloping a black hole, I prove that this would violate causality. This would allow you to send information into your own past light core. So this is something that is impossible. But as far as ADS-CFT complementarity, no problem. No problem with this.
Okay, yeah. You know, it's interesting too, because there's like different versions that like use that kind of membrane idea, as you say, more than others. I don't know. I think you're right that it's not quite.
And the reason for it, without going into detail, very simply is that black hole complementarity, and you have to be careful. There is black hole, there's the holographic principle, which is the ADS-CFT complementarity, and there's black hole complementarity, which tells you that there's a membrane surrounding the event horizon. The problem here is that the event horizon is a teleological concept. It is not known what it is until time plus infinity. So right now, you cannot, I don't know if I'm in front of an event horizon, if there is one right here, if there's not one right here. I will have to wait until time plus infinity before I know where the event horizon is. And if there is a physical membrane surrounding the event horizon, then if it is a physical membrane, there should be a way of testing it. Okay, here is a physical membrane. And if the physical membrane is here, then the event horizon is here. But the event horizon is not known until future infinity. So there's obviously a contradiction.
Yeah, I can see how like that might present a problem. I mean, like, I don't think that, like, I know there's some papers by like Susskind that I've read where he like explicitly employs this sort of like membrane idea, which I don't know if that's necessary in all formulations of black hole complementarity. And the other thing I wonder about is, I mean, I see your point about the event horizon being difficult to define. I mean, could you say something about like how that relates to the fact that it's in any case relative to like some outside observer who's like some stationary.
To the Schwarzschild observer, the event horizon never forms.
Let me present it in a somewhat different way. Suppose I have a collapsing shell of dust, and suppose it collapses into a black hole. In this case, the event horizon will start at the center of the shell of dust long before the black hole has formed. Because by the time the shell of dust has reached the Schwarzschild radius, the event horizon, which starts at the center of the collapsing shell, has exploded all the way into the Schwarzschild radius, and it has exploded at the speed of light. Now, suppose that at the center of the collapsing shell of dust, it's a big shell of dust, huge. And at the center, I have a neutron star. Then the event horizon that starts, in this case, at the center of the neutron star, expands through the neutron star at the speed of light. And as it does so, it absorbs within it all the information in the neutron star. So if it has information in it, it has energy. If it has energy, it has mass, and it still expands at the speed of light in the gravitational field of the neutron star. I would say, if you buy this, I have some bridges to sell you.
Huh. I mean, I'm not sure if I totally understand exactly what you're saying, but like, is it, I mean, it seems to me that, I mean, I don't know. I guess like the reason black hole complementarity makes sense to me is it just seems like a way of saving like the equivalence principle, right? Like you somehow want some way of saying that like, look, an event horizon, a black hole, it's a gravitational phenomenon, right? It's a space-time phenomenon. And what that means is that like, if you were just there, you would experience it as just free fall, right?
No.
Like, that's the deep thing, you know?
Principle. The reason for black hole complementarity is to save information.
Saving what?
To save information, to resolve the information paradox.
The only thing it saves is Suskind's career.
That was in a black hole. Suppose we have a star that collapsed into a black hole. The star has within it a huge amount of information. Where did all the information disappear? And then it can reappear in the Hawking radiation. If it is inside the black hole, in the singularity, there's no way you will sit in the Hawking radiation. So the way out of it was, okay, the information does not really fall into the black hole. It stays outside the black hole. Well, there is a membrane just outside the event horizon, and this is all the information.
No,
is
no, no.
left.
Well, I mean, I'm sure that's how some people have tried to formulate black hole complementarity. But I mean, most of them aren't saying that there's like literally like a membrane that surrounds the black hole and that's where the information is. They're saying that it's like an extension of the equivalence principle, that like, you know, the idea of something being inside the black hole and the idea of something being outside the black hole are just two different perspectives on the same thing.
Susskind says that there's an extended membrane about 1 Planck.
Yeah, there are some papers where he says that, but like, frankly, most of those are from the 90s.
Yeah, that's right. You're absolutely right. Suskind's original paper is from the 90s. He has some subsequent papers 10 years later where he talks about actual membranes surrounding the black hole. And of course, there's lots of theories that do not have a membrane surrounding the black hole. For instance, I never heard Maldacena claiming that there's a membrane surrounding the black hole. What Maldacena says is there's a correspondence between ADS and CFT.
Yeah, so I think we're in agreement then. I mean, I think, yeah, there's probably problems with the membrane idea. I mean, I figure, you know, it was probably like a useful.
So Moshe, let me ask you, if a black hole can destroy particles, why is it so important to preserve information, but not particles? I would be asking Susskind this question if I could reach him.
It's the same thing. The black hole destroys information.
Well, but that's not what Susskind believes. That's not what Hawking believed.
The initial view of black holes was that they destroy information. This is the essence of black holes have no hair. All the information is disappeared. All the information is vanished. The number of baryons that fell into a black hole has disappeared. You don't have this information. You don't know how many baryons fell into the black hole. And this is something that really concerned lots of people like Susskind, and they try to come up with some solutions to this.
So how can a black hole have entropy if the information is destroyed?
Well, yeah, as a counterpoint to that, you know, I just was thinking, I never shared this with you guys, but actually, I remember, you know, just like, I think it's worth questioning the theory of black hole complementarity. Like, I like it, but again, loop quantum gravity is yet another theory where, you know, the story is quite different, and their story about how information or unitarity is preserved is different. And in fact, even within the loop quantum gravity community, there is disagreement. And you know, what I was given to understand is like, there's actually two camps in a way. One is that, you know, holds that at some point, you know, stuff falls in a black hole, and then the black hole kind of itself collapses and bounces back to like a white hole that just spits everything back out again, which is then, of course, you know, the same math that they apply to try to apply to the Big Bang, which they're going to look at as a big bounce. But I actually thought the more interesting theory was the idea that stuff falls into the black hole, it gets scrambled up, but that, like, because remember in loop quantum gravity, space-time is described by like these spin networks, right? And so there's like all this like fine-grained like quantum structure at very, 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 very small scales, right? Like practically Planck scales. And, you know, to use a metaphor, there's a kind of weave to space-time, like, you know, quite like in a loopy kind of way. The idea is like space-time is like woven out of these spin networks. And so the you know, one idea which I thought was quite nice, I mean, I'm not saying I can like evaluate whether it's true, but I was like, it's a nice concept, right? Is that, you know, like imagine you have like a smooth weave of space-time. Oh wait, I wanted to draw on the board. No. Oh no, you can already see that. Oh no, I see what's going on here. Yes. Where's my purple? It's like you start off with like a smooth weave of space-time, and then, you know, like a black hole forms or something, like, you know, and it has the effect of like tangling it up, okay, and fucking with the weave of space-time. And then the idea is like the black hole like evaporates. But after it evaporates, it like leads to tiny little like weird imperfections like in the weave of space-time that are at a scale, and you'll love this, guys, that are at a scale too small to ever detect. Okay, right? You know, so it's like, where does the information go? It's like, oh no, it's still there. It's like in the quantum state of the spin networks that like
violates Landauer's principle.
But it's
violates Landauer's principle. You need information is physical. You can't store information in empty space.
Well, in these theories where you have actual quantum states of space-time, right? Like, you know, this idea of like space being kind of glued together out of these quantum polyhedra that are like themselves quantum states. So like that's their approach to quantum gravity, like straight up.
But it doesn't mean you can store physical information in them. You need a physical material to store physical information. Maybe they have a state. They have a state, but not information.
I don't know.
You can't store information that was physical and non-physical.
A gravitational wave. Is that not information?
Yeah, but that's energy.
Yeah.
Gravitational wave is energy. It's stored, the information is stored in the energy. Energy and matter are the same, E equals mc squared.
Yeah.
But you can't store information in empty space, even if they are composed of spin networks.
Well, it's stored in the connectivity of the space, right? So it's like the space kind of spaces we're used to are like the smooth spaces where you have just like a smooth quote unquote like weave.
Well, a similar theory of black hole evaporation is that at the end of the evaporation you have a small remnant in which all that information is contained, but it's still a physical remnant.
Yeah, so this is similar, but it's where like basically the rug of space-time has become a little bit tattered by the fact that a black hole had like formed and then evaporated. And to do the theory justice, I should say, I mean, it's not, they weren't claiming that like this is just, and this is great because it's unmeasurable. They were just sort of like, the point, right, was that you would have a, you know, like if you could imagine the weave like a cross stitch or something, right? That's kind of nice, right? Because here there's 4, you know, things coming into a node, and so you can imagine like a quantum tetrahedron, you know, sitting at each of these vertices, right? But we're talking about like a very tiny scale. And so like the idea is like after, you know, the black hole has sort of fucked up this space, it's like, well, maybe now like this tetrahedron's glued to that one, and this one's glued to that one, and this one's glued to that one, and this one's glued to that one. And so at the very tiniest scales, there's these imperfections in the textile of space-time, which is basically like where all that information that fell into the black hole has now manifested itself. It's just
well, this is
larger scales, like at the normal scale of like, you know, things like normal things. This stuff's so tiny, it's just like would be really, really hard to measure it, right? So, and now they weren't saying that there was like no way to measure it, like, but that you'd have to measure it by proxy. But the point was to say something like, well, we have a situation where like a black hole evaporates. Where did the stuff like that was in it go? And you know, because it doesn't seem like it's anywhere. And the idea was like, it's encoded in slight imperfections in the underlying weave of space-time.
Matt, let me
Okay.
make a suggestion. You may want to go to YouTube. Put my name in YouTube. There's only one item that I ever posted there. This is a session that we had at the New York Quantum Theory Group several months ago, maybe a year ago. And it presents a very simple picture of black hole information, how the information is instantiated inside the black hole, how it is preserved inside the black hole, how it emerges out of the black hole, why it is so mixed up inside the black hole. It also explains very easily why charged black holes are very eager to lose their charge. The mechanism by which a charged black hole gets rid very quickly of its excess charge. And a few other things like this.
Where does the charge go, Moshe?
It is being radiated away. It shows you.
Well, what do you mean by radiated? It's got a charge can only exist in a material, in a massive particle.
Yeah, that's right. It gets radiated in electrons and positrons and whatever. Charged particles coming out of the black hole and they carry the charge away.
All right, well, see, all of this discussion is based on the unfortunate legacy of Leonard Susskind,
And also,
I like Lenny's.
who refuses to accept that information can be destroyed. He refuses to accept that information can be destroyed.
True. Yes.
And
Great.
a lot of Hawking, originally, when Hawking came up with the Hawking radiation, in fact, he made a bet.
I mean, I'm pretty sure
Information
that
is
Hawking
destroyed.
stopped believing that information was destroyed sometime around like 1978.
What's that?
I'm pretty sure Hawking stopped believing that information.
He stopped believing it
sometime by the
because
late
it was-
70s. I mean,
It was pressured by
No.
Susskind and other people. You know who? Preskill. You know who has never accepted it? Kip Thorne. Kip Thorne has stuck with Hawking's original premise that information is destroyed. But Susskind
I
has
was
such
genuinely
political
curious.
influence.
I don't even, I was like trying to name, like, I don't even know any physicists. I'm glad that you mentioned Kip Thorne, who actually think that information is destroyed. So
I
it's
mean, that
interesting
it can be
Kip
destroyed.
Thorne would say that, yeah.
There's also another thing, the false equivalence of thermodynamic entropy and Shannon entropy. The assumption that they're both the same. I don't accept that.
Yeah, yeah. So the loops people actually play around with that. So they are, yeah, in the loops picture, they actually think that the entropy of the black hole is proportional to the volume, not the surface area, and give a different explanation of the Beckstein-Hawking, whatever, entropy relationship. So yeah, I mean, you're right. That's not universally agreed upon.
Well, I think black holes have zero entropy. That's my opinion. I think the information is destroyed. Hawking was correct originally, and he should have stuck to his guns. A lot of people think, some people anyway, think he should have stuck
Does
to his
that,
guns.
in your mind, connect up with your sympathy towards Bohmian mechanics? I mean, because like to say the
There's
information
nothing to do with it. There's
is
nothing to do with it.
well, it's to violate, you know,
No, but
Bedrock
the thing
principle
is,
quantum
the thing
mechanics.
is physics,
So, I mean,
physics is not a popularity contest. Science is not a you know, 100% of physicists believe in the phlogiston theory 300 years ago. Didn't make it right. Science is not a popularity contest. And because the people with political influence in the scientific community have persuaded 99% of the others to
but I
go
mean,
along
it's
with
like a
them, doesn't
general
make it
physical
right.
thing here. You're saying like nothing can disappear from the universe unless it's like going somewhere.
I didn't say nothing can disappear. I said information can be destroyed. And a black hole, to me, is a dead object. It's got zero entropy. And by the way, that's what Wheeler said. Wheeler said, you know, Andre brought this up about a black hole having no hair. That was
Yeah, but I mean, but that's like
Wheeler's
ancient history.
premise.
And that's like, I mean, that's like, that was during, all that stuff comes out of, you know, the revival of general relativity in the 1960s, like leading up to like all these like early kind of semi-classical calculations of Hawking and others in the 70s and stuff. I mean, that's like the prehistory of like all the stuff that everyone does now.
But why does everybody assume that that information cannot be destroyed? Because Susskind said so? Susskind is not God.
Because, you know, the idea is that we like to look at the universe as a whole as a closed system, and therefore probabilities have to sum to 1 in the one accurate, you know, formalism that we use to describe nature. I mean, it just seems like there's a lot of extra stuff you'd have to assume, you know, like if you were trying to say that information was in fact destroyed. I mean, it's like saying probabilities don't sum to 1. I mean, it's like,
I
you know,
don't see the again. You're confusing thermodynamic entropy with Shannon entropy. That's a whole other. That's the other assumption they all make.
what do you mean? It's like thing has a quantum state, and then if it becomes inaccessible to me, like what do? I partial trace over it. But the idea is like, sure,
Inaccessible to you does not mean inaccessible to the universe. Thermodynamic entropy says that the information is inaccessible to you, but theoretically it's accessible.
I see what you're saying. Right. Yeah. So, okay, that's fine. I mean, like that I could see, right? Like you could be like, here's the universe, and then there's these like abscesses. There's just places where shit's gotten trapped, never coming out. It's just there. It's just done. It got there because it fell into a black hole. The black hole evaporated, and now this little fucker's in like a cul-de-sac of reality, and it's just there in this like little hell for all eternity. This seems to be what you're saying.
You know, you have to go back to the basic definition of what is entropy. What is thermodynamic entropy? It's how many ways can you put together a microstate to give you the same macrostate?
Yeah.
And that doesn't apply to a black hole. In a black hole, every black hole that's the same size is exactly the same. There's only one microstate. There's no multiple microstates. There's only one microstate that equates to the macrostate. Therefore, the number of combinations is 1. K log of 1 is 0. The entropy is 0 for a black hole.
You say that on the basis that nothing can come out of it, so that no one could distinguish between different.
Even aside from the fact whether or not, no, Hawking radiation is a whole separate issue. But Hawking radiation is black body radiation, which also has no information. Black body information has no information, and that was Hawking's original belief. And why he changed his mind had more to do with politics than science, quite honestly.
It's possible.
The politics of the, physics community. Led primarily by Susskind, who I think is dead wrong.
It's like, but how do you deal with one of the cool things about like the ADS CFT stuff is that like it's not just like a model of like a black hole where you're like, okay, got the conformal field theory on like whatever, maybe it's a membrane, if you want to look at it that way. And then you got this gravitational theory.
Maybe it's a surface. Maybe it's a surface.
But they actually use the model to be like, what if you have other black holes in the ADS space?
Look, ADS CFT
so like,
is not physical. It is a mathematical construction
right,
that lets you solve problems.
Right, but what you can do is you can say like, okay, here's the CFT, the ADS space in the interior, and then like, what if there's like black holes in there? Now, like people in the ADS space, they're like, oh my God, it's a black hole, something fell in, like, oh, is it gonna come out? I don't know. But all of the information in here is on the surface of the CFT. And so, you know, people who are like out here are like, oh yeah, like this, everything that's in this black hole and also the stuff not in this black hole is described by like this region.
Look, Matt,
The whole idea is
with all
like,
due respect, what you're talking is math. You're not talking physics. ADS-CFT is a mathematical construction that enables you to solve certain problems in QFT, you know, by solving it in the bulk.
well, I'm just
It's
saying,
a
it's like,
mathematical construction. There's no such thing as six-dimensional
I mean, I
physical
could say the same
space.
thing. I could say like your assertion that like the black
assertion
hole
could be
has
completely-
zero entropy is just also like a mathematical.
My assertion could be completely wrong. But the thing is, to assume that information cannot be destroyed, to me, doesn't make any sense. And like I said, going back to the original definition of Clausius or Boltzmann entropy, thermodynamic entropy, it's how many, if you have a cylinder of gas, how many different ways can you put together the positions and momenta of the molecules to give you that macrostate? That's the definition of entropy, K log W. With a black hole, there's only, there's only one microstate that gives you the macrostate. So the entropy is zero by definition.
Well, but like, so
And again, entropy is entropy is a mathematical definition.
sure, but
You
so like,
can't
in
measure
the
entropy with an entropy meter. It's a mathematical description.
but like in the yeah, like in the loops picture, right? It's like the microstates are these spin networks and spin foams and so forth, right? So like in that theory, you know, like that's their whole philosophy, right? So like, whereas the black hole complementarity people like start from things like the surface area entropy connection and ADS-CFT and all that, which try to kind of like make these very general statements and then don't really necessarily say anything specific about the supposed microstates of the black hole, which you then end up modeling with like whatever qubits. You're just interested in scrambling more generally. And I mean, they get more specific, obviously, too. But, you know, the loops people pride themselves on being like, we have the theory of the microstates of spacetime. They are quantum tetrahedra and quantum cubes and quantum these little polyhedra and whatever.
And they stole that idea from Plato.
Aha. Yeah, sure. No, I mean, yes, Rovelli, in fact, yes, includes, you know,
Yeah.
images of the Platonic solids in his book, of
And
course.
since there's no way to test this physically, there's no way to test any of these theories physically,
Well,
you know, then what
well, no, I mean, you
use
could,
are they?
in
Except as
theory,
mathematical constructions that might help you to solve physical problems, but they can't be taken literally.
well, again, the loops people, you know, propose two kinds of experiments, some being of the sort of like, can we put like masses and superpositions and try to see like which theory better predicts like various disturbances of the wave function. But then, you know, the more interesting ones were like at some point, you know, even at large scales, depending on your underlying theory of gravity, you know, you're going to get divergences from, you know, general relativity. And the loops people hope to see in the sky evidence of their theory.
And whatever they come up with, there are so many alternative theories that
Well, that
explain
would
these
this would
things.
be evidence for in their favor, right? Like that's their whole idea.
Like the fact that, you know, Newton's law of gravity or even Einstein's law of gravity is only an approximation and it doesn't apply throughout time and space. There's so many different ways that they can explain these things with alternate mathematical theories. And, you know, with something like black hole complementarity, what a convenient theory. Because
I don't believe that, right? That's their whole thing. They're like, they very sharply distinguish themselves from the black hole complementarity.
Okay, but I'm just
And
saying as an
trying to figure out
example.
what exact predictions would like loops have that, you know, whatever the other people don't, string people don't, right? Like that was the classic thing, right? Loops versus strings, blah, 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 blah. That flame war has died down, I would say, somewhat in recent years. But that was the whole point, right? It's like they're all like super invested in like trying to find experiments that would like actually prove their theory right, as opposed to
If there is an experiment they can design to test it, then it is science. But something like black hole complementarity, which the presumption is that you can't know what's going on behind the event horizon. So it can't be tested. And if you fall through the event horizon, then you can't find out what's going on outside.
I mean,
It's a
unless
ridiculous
you do.
theory because it can't be
man.
tested by definition.
For all we know, there's the mouth of the wormhole, you know, hanging behind the moon, and then we fly our spaceship
Yeah, right.
over by
And,
Jupiter. Hey, I'm reversible wormholes. You know,
like
yeah,
you
you're-
said,
the
I have a
ultimate
bridge
test
to
is-
tell you.
The
I have
ultimate
a
test,
bridge
I
to-
agree with you, is you gotta send something through the wormhole. You gotta
Too many,
follow it
too many
yourself.
physicists.
Right, it's not even like, I would say it's an interesting like sort of empirical thing, right? Because just because you have this, you watch something fall into a black hole and then it pops out another black hole later, right? You could just be like, well, that could happen in many ways. Maybe it's just like it's more abstract, like quantum teleportation or something. Frankly, yeah, from at a really, really deeply empiricist level, you'd have to go into that wormhole yourself to confirm that geometrical interior really did exist.
Which
If you're
which
really
doesn't
serious,
prove anything because when you go in, you can't get out. So of what use is it?
Well, no, I'm
What I'm
saying-
saying is this is not science. This is all conjecture. Science is something that can be tested with empirical
That's what I'm
evidence.
saying. There is evidence, many of these theories present evidence that wormholes can be traversable, as we've talked about, under the right circumstances. But yeah, I mean, I agree with you that is only gets to be written in the annals of fact, not just when you throw something into it and it comes out, but when you yourself fly into the black hole, experience some geometry, and
And you'd have to
out.
come out.
You have to do it yourself. You really
Yeah,
do. Like, you know what I mean? Like, to know that it's there. Because
Why
otherwise,
would anybody
just be
want
like,
to do
oh,
that?
there's some other thing going on. It's just the thing. Just because something disappears here and reappears there, does that really imply that if you yourself fell into it, you would just be in this kind of like weird space-time that's like,
Now I just got some communication from Washington D.C. If you pour hydroxychloroquine on a black hole, it will answer all of your questions.
yeah, exactly. It's
Another scientifically valid assumption.
Yeah, what does Donald Trump think about black? I mean, I hate that Donald Trump has the honor of being our first quantum president, having established all these quantum.
Donald Trump
Doesn't
is
deserve it.
symptomatic. Donald Trump is symptomatic of where this country has been going for my entire life. Donald Trump is the symptom, not the cause of his existence.
Oh yeah.
And, even if he's defeated, and that's going to be a big hassle, even if he's defeated, we're not over the problem that this country suffers from.
Oh, yeah.
This country suffers from anti-intellectualism. It has, for most of its existence, actually, where they tell us, where we celebrate people who dropped out of junior high school and became billionaires. That's who we celebrate.
Right.
Unlike the European and Asian models where they celebrate education, we denigrate education. It's like, oh, he's a billionaire and he never even went to junior high school.
Yeah.
That's
That's
the problem we face. And Trump is just the symptom, a very dangerous symptom. But he's just a symptom.
It's the equation of money with value of a person.
Yeah, and it's like,
Well, that's what you think Trump even has money.
democratic, but like at the same time, it's not. It's not.
You know what Trump is? Trump, you and I are worth more than Trump is. This is why he won't release his tax returns, and it's becoming more and more obvious because
A penny.
he has a negative net worth.
Oh, yeah.
You know, it's the old line: if you owe the bank $1,000 and you can't repay them, who's in trouble? You're in trouble. But if you owe the bank $1 million or $1 billion and you can't repay them, who's in trouble? The bank's in trouble.
Yeah.
Not only that, they'll keep revolving your loan, the false expectation that you'll repay them. That is the whole structure on which the Trump organization is built.
Sounds good.
You know, in the old days, the old man Trump was there to bail him out of all of his bankruptcies. The old man's not there anymore to bail him out. Now it's all smoke and mirrors, and the banks play along with it because they don't want you to know how stupid they were to lend them.
Yeah.
Yeah, exactly. Yeah, to be on the fly on the wall. Probably just.
Well, you don't have if you're smart, you can figure it out. If you grew up in Brooklyn like I did, you know all about the Trump family.
Oh.
You know, that's where they did
Yeah.
their business. That's where they did their business, and you know all about them.
I grew up there.
So you didn't know about them?
Oh, no, I did. And I hated them for, I don't know how many years, decades. Yeah. They're constantly ripping off their own contractors and all, not paying them.
They didn't pay. They were the last real estate organization to integrate their
Oh, yeah.
buildings.
Yeah, that's
They had a consent decree with the Justice Department to integrate their buildings, and they violated that consent decree. They should all be in jail for violating a consent decree with the Justice Department. But, you know, when you're rich, it doesn't work. When you're rich, you just pay off. You pay the fine.
yeah,
You continue
exactly.
same old way.
Yeah.
And
Yeah.
That's why bribery is illegal, supposedly.
well, only for poor people.
Oh, yeah.
Bribery is the
If it's not
the
enough
way,
money.
is the way rich people do business. Our
Ah,
political system is based on bribery,
yeah.
and I don't care if Trump is elected or the other old guy. You know, it's the same old until they get money out of politics.
Right. Yeah.
Forget
As soon
about
as Citizens United came online, I knew that it was all over.
Well, you know, but it was long before Citizens United, and even if Citizens United is struck down, they'll find ways around it.
Yeah. Oh, that's true.
You know, Marty, when you and I were born, you know who the congressman from Brooklyn was? Emmanuel Seller. I don't know if you remember
No,
that name.
no.
Maybe a little bit before we were born. He was this long-term congressman from Brooklyn. His campaigns cost something like $200 every time he ran for re-election.
Wow.
Now Congress people have to spend 70% of their waking time raising money
Oh, yeah.
to run for their next election.
Oh, yeah.
So that
Yeah, I remember reading an article about it where, like, yeah, it was like practically they lived the life of someone working at a call center.
Yeah.
Like,
or somebody
it's a weird
working
way
in
that the circle completed itself.
or somebody working in a whorehouse.
Oh, that's two.
But you know why Charles Schumer is the Democratic leader? Not because he's the most beautiful or the most articulate, or he's the best money raiser.
Ah.
Because instead of spending 70% of his waking hours raising money, he spends 95% of his waking hours raising. That's why they elected him the leader.
See.
Mitch McConnell, I don't know what. Well,
Wow.
he must raise a lot of money too. I don't know.
Yeah,
He's got a rich wife. He's got Elaine Chao, and they own the whole blocks in Seoul, Korea, or
Yeah,
whatever it is.
That's true. Yeah, at least Schumer is married to a poor woman. I dated a girl a long time ago who was friendly with Schumer's wife when they were both in high school.
Ah.
His wife though is a political incompetent. You know, his wife was the transportation commissioner under Bloomberg, and she totally fucked up. And they had to get rid of her. She was an embarrassment. Iris Weinschel.
You said under Bloomberg?
Under Bloomberg, yeah. Under a Republican mayor. Schumer's wife was the first transportation commissioner. They had all those crashes on the Staten Island ferry, and it turned out all the Staten Island ferry pilots were drunk at the wheel
Yeah,
or drunk at the rudder.
sure.
And by the way, Elaine Chao was transportation commissioner.
Right, yeah.
Is transportation commissioner.
Huh.
After that, all those Boeing 737 crashes that she did nothing about, that she
Oh,
took no responsibility for, why hasn't she been fired?
Makes you think.
Let alone
Hmm.
prosecuted. They let Boeing do its own approvals on its its own
Oh,
safety
yeah.
approvals, which they let
Okay, I
drug
have to
companies do
leave,
too.
guys. Good talking to you, and Matt. A million
she's bored.
thanks. Really appreciate. And I
Yeah.
realize that you've been doing tremendous amount of work, and I really appreciate
True.
this.
Yeah,
Thank
Oh,
you.
yeah.
Moshe. Yeah, and thank you for your presentation.
See you
Bye.
tomorrow, Moshe.
Actually, I'm sorry about it. I regret that I did this presentation because it was less time of your presentation.
Ah.
I didn't.
I liked your picture. It was cool.
We'll get even tomorrow.
Oh,
Don't
Moshe, what's your last name so we can look you up on YouTube?
Rosenblit.
Oh yeah, I think I
Rosen-
found the video. I'll send it to the.
Oh,
Yeah, my last name is Rosenblit.
okay.
R-O, what is it? ROZENBLIT?
That's correct.
Okay.
And it is really amazing how using only general relativity and quantum field theory and absolutely nothing else, no additional ingredients, no additional assumptions, you get a very clear picture of how information is preserved inside the black hole, how it comes out, why a big black hole is cold and a small one is hot, and all kinds of other things. And by the way, Maldacena did not object too much to it. Maldacena had one objection, and when I spoke earlier today, I was basically addressing Maldacena's objection.
Mm.
What I said earlier today is because of Maldacena's objection.
Gotcha.
So if you have a chance to look at it, I would really appreciate your comments.
Okay.
Yeah,
It
definitely.
would be great. Okay, see you guys. Hope to see you next week. Bye.
Bye.
Yeah, I should probably go too.
Yep.
It's been great.
I'll talk to myself. That's okay.
Yeah. But yeah, stay safe out there. That coronavirus is picking up. Third wave.
Yeah.
Well, stay safe
that's true.
inside. You're more dangerous inside if you're with people,
Very true.
even your own family.
You can't trust anyone.
Yeah.
Well, it's not a matter of trust, But it's gonna
Yeah.
it's gonna
No.
come back. It's gonna come back even worse in the winter.
Yeah. No, it's crazy. I mean, I expected to reach the level we reached in July by like election day, but it's only October 24th. We already exceeded.
Well, the thing is, there's been an utter failure in dealing with it.
Yes.
The leadership of this country is in utter denial.
Oh, yeah.
Yeah. It's really.
And but every pandemic, there's usually a first wave, and everybody gets complacent when it dies down, and then the second wave is more virulent. But our second wave is going to overlap with the first wave because we never dealt with the first wave.
Yeah.
But eventually we'll run out of idiots.
Well,
Yeah.
that actually is the policy. The so-called herd immunity is the unofficial policy of this country.
Yeah, for real. It's
Right.
basically like, okay.
But the thing is, it may not work because we don't know that if you've been infected, we don't know for how long it gives you immunity.
Yeah, that's true.
So the whole concept of herd immunity may not work for this. In
That's
fact,
right.
there are documented cases of reinfection.
Oh, yeah.
So this is not the measles. You know, herd immunity is not going to work. But that's what the unofficial policy is. And by the way, it's official now because this idiot doctor that
Oh yeah, Atlas.
Atlas, yeah, he has proposed herd immunity. He believes in it.
Yeah, it's just.
That's why he was hired.
But this has been
Yeah.
He's a contractor.
this has been the policy right along, the unofficial policy. And by the way, it was the policy in Sweden, the official policy, and it failed.
Yeah, it failed.
And Boris Johnson in the UK proposed it at first, and he was basically laughed out of town, or he had to change his policy. But we have the highest infection rate in the world.
That's
Worse than third world countries, worse than Pakistan.
Yeah. Well, and it'll be interesting to see this current situation since the previous waves, so to speak, were, I mean, they were localized. You know, you could be like, New York, or you're like, whatever.
Well, the thing is,
what you don't like has it, or like whatever, depending on who you are. But now
New York
very,
is
like, everywhere.
New York is like a different country. I will say that Cuomo and de Blasio both dropped the ball in the beginning, but eventually they got their act together. But you know what it is? When I walk out my door, everybody's wearing a mask.
Mm-hmm. Yeah.
yeah.
You can count the people without a mask on a few fingers.
Yeah.
Everybody's wearing a mask on the streets of Manhattan. You don't have that in the rest of the country. And that's the problem.
Yeah. Even in Philly, it's like most are.
Yeah. Okay, because these are the better educated populations. Most of this country are a bunch of dumb fucking idiots.
I'm going to make a background of coronavirus particles wearing MAGA hats.
They're all already wearing them.
All right, guys. Gonna head out.
Next time.
Yes. Yeah.
Till next time.
Have a
Bye.
good one.
Thanks very much.
Don't get discouraged just because I'm
No.
I was negative when I came out of the womb. Don't go by me, you know.
No, without you, you know, where would we go? You know what I mean? Gotta keep the.
And also, you know, you have to question everything. The best
I agree.
the best advice, especially if you're a scientist. The major breakthroughs in science have all been made by people who question the orthodoxy.
Yeah.
You know, and that's the nature. And again, it's basically hope for the best, but expect the worst when you live your life.
Crazy relationship that, you know, there's such breathless
I'm
excitement
going.
about results and
Let's
gravity
see,
and
leave.
the little experiments. That's really.
I'm leaving.
All right. See ya.
Ciao.
Ciao.